The following is a conversation with Konstantin Batygin, planetary astrophysicist at Caltech, interested in, among other things, the search for the distant, the mysterious Planet 9 in the outer regions of our solar system. Quick mention of our sponsors, Squarespace, Literati, Oort, and NI. Check them out in the description to support this podcast. As a side note, let me say that our little sun is orbited by not just a few planets in the planetary region, but trillions of objects in the Kuiper Belt and the Oort cloud that extends over 3 light years out. This to me is amazing, since Proxima Centauri, the closest star to our sun, is only 4.2 light years away, and all of it is mostly covered in darkness. When I get a chance to go out swimming in the ocean far from the shore, I'm sometimes overcome by the terrifying and the exciting feeling of not knowing what's there in the deep darkness. That's how I feel about the edge of our solar system. One day, I hope humans will travel there, or at the very least, AI systems that carry the flame of human consciousness. As usual, I'll do a few minutes of ads now, no ads in the middle. I find those get in the way of the conversation. I try to make these interesting, but I give you timestamps, so if you skip, I hope you don't, but if you do, please still check out the sponsors by clicking the links in the description. It's the best way to support this podcast. I'm very picky about the sponsors we take on, so hopefully if you buy their stuff, you'll find value in it just as I have. This show is sponsored by Squarespace, a new sponsor for the podcast, but I've been using their stuff for many years now. They make it easy for you to make your own website. In fact, for the 4x4x48 challenge with David Goggins, which happened in the spring of 2021, I was talking to David on the phone, and I suggested I could make a website for the challenge very easily using Squarespace. And that's how gogginschallenge.com was born. Now, that particular website was used only for a few months, and then we set it back to private. So it was mostly used to give information about the challenge and to let people submit their stories of successfully finishing the challenge. And we got thousands and thousands of submissions. It was quite incredible, actually. The number of people that David inspires is just, it's truly humbling. But the point is, on the website side of things, it was super easy. It's an all-in-one service because you can also register a domain. You can do e-commerce kind of stuff. Really anything you want from a website, Squarespace has it. Go to lexfriedman.com/Squarespace for a free trial. And when you're ready to launch, use the offer code LEX to save 10% off your first purchase of a website or domain. That's lexfriedman.com/Squarespace, and that should forward you to the right place. This show is also sponsored by Literati Book Clubs. Join book clubs hosted by people like Richard Branson and Stephen Curry, but there are many other ones. They deliver their monthly book picks straight to your door. I personally am part of the Joseph Campbell's book club called Myth and Meaning. One book I read in that club is The Spell of the Sensuous, Perception and Language in a More Than Human World. David Abram, the author, describes beautifully how we have become disconnected from nature and how we can reconnect while still remaining in the modern world. I think there's a lot of people that write books like this in an almost naive dismissal of all the amazing things that technology brings. David doesn't do that. But he does highlight that there is things to be discovered in the other than human if we were sort of open our senses to them. That's what nature is. Life all around us that isn't human. Anyway, reimagine what a book club can be. Redeem your 30-day trial for only 99 cents at literati.com/Lex. Head to literati.com/Lex to learn more. That's literati.com/Lex. This episode is sponsored by Oort, nutrition, supplement, and fitness company. They make Alpha Brain, which is a nootropic that helps support memory, mental speed, and focus. I use it as a kind of boost for my mind when I'm thinking about a difficult problem. So if a particular deep work session requires just like sitting there and thinking with a sheet of paper, usually that's kind of like the design stage for the idea, when it's purely thinking. That's usually when I, for a prolonged period of time, have to turn my mind to 11. So it's focused, but it's also like actively digging deep. That's how I think about thinking. It's like digging a hole, searching for gold. And most of the times you come up with nothing. Speaking of digging, There Will Be Blood is an incredible movie. Not only is one of the greatest actors in history, but he's also one of the most interesting actors in history. The few interviews with him that I've seen, you can tell it in his eyes. There's brilliance there. I'm not sure why I brought that up. I think it had to do with digging for gold. But yes, I use Oort to help me dig for gold, but in the space of ideas. It clears the mind, maintains focus, that kind of stuff. Go to lexfriedman.com/Onet to get up to 10% off Alpha Brain. That's lexfriedman.com/Onet. This show is sponsored by NI, formerly known as National Instruments. NI is a company that has been helping engineers solve the world's toughest challenges for 40 years. Their motto is engineer ambitiously. I love listening to podcasts, so I'm excited that NI has a new podcast called Testing 123. I love that name. They bring on engineers and innovators to discuss unexpected challenges and explore the world through the lens of testing. In the parts of my work that involve software engineering, I love the process of testing. I mean, you can think even just the debugging process is a kind of process of testing. And that first few moments when you run into problems, into warnings, into errors, that's such a special moment because you're catching problems in the code, thanks to the debugger, that could have been much more painful, much more costly if they were encountered in the application of that code in the real world. Anyway, NI's new podcast called Testing 123 is all about that. You can get it at ni.com/perspectives. They also have a bunch of amazing articles on there, or you can get it basically anywhere podcasts are available. That's ni.com/perspectives, and the podcast is called Testing 123. This is the Lex Friedman podcast, and here is my conversation with Konstantin Batygin. What is Planet 9?
Planet 9 is an object that we believe lives in the solar system beyond the orbit of Neptune. It orbits the sun with a period of about 10,000 years and is about 5 Earth masses.
So that's a hypothesized object. There's some evidence for this kind of object. There's a bunch of different explanations. Can you give like an overview of the planets in our solar system? How many are there? What do we know and not know about them at a high level?
All right. That sounds like a good plan. So look, the solar system basically is comprised of 2 parts, the inner and the outer solar system. The inner solar system has the planets Mercury, Venus, Earth, and Mars. Now, Mercury is about 40% of the orbital separation of where the Earth is closer to the sun. Venus is about 70%. Then Mars is about 160% further away from the sun than is the Earth. These planets that we, one of them we occupy, right, are pretty small. Okay, they're to leading order, sort of heavily overgrown asteroids, if you will. Okay. And this becomes evident when you move out further in the solar system and encounter Jupiter, which is 316 Earth masses, right? 10 times the size. And Saturn is another huge one. It's 90 Earth masses at about 10 times the separation from the sun as is the Earth. And then you have Uranus and Neptune at 20 and 30, respectively. For a long time, that is where the kind of massive part of the solar system ended. But what we've learned in the last 30 years is that beyond Neptune, there's this expansive field of icy debris, a second icy asteroid belt in the solar system. A lot of people have heard of the asteroid belt, which lives between Mars and Jupiter, right? Like that's a pretty common thing that people like to imagine and draw on lunchboxes and stuff. Mm-hmm. But beyond Neptune, there's a much more massive and much more radially expansive field of debris. Pluto, by the way, it belongs to that second, icy asteroid belt, which we call the Kuiper Belt. It's just a big object within that population of bodies.
Pluto, the planet.
Pluto, the dwarf planet, the former planet,
Why is Pluto not a planet anymore?
I mean, it's tiny. We used
So
to
size matters when it comes to planets.
100%, 100%.
Mm.
It's actually a fascinating story. When Pluto was discovered in 1930, the reason it was discovered in the first place is because astronomers at the time were looking for a 7 Earth mass planet somewhere beyond Neptune. Okay, it was hypothesized that such an object exists. When they found something, they interpreted that as a 7 Earth mass planet and immediately revised its mass downward because they couldn't resolve the object with the telescope. So it looked like just a point mass, star rather than a physical disk. And they said, well, maybe it's not 7, maybe it's 1, right? And then sort of over the next, 40 years, Pluto's mass kept getting revised downwards until it was realized that it's like 500 times less massive than the Earth.
Yeah.
Right? I mean, like Pluto's surface area is almost perfectly equal to the surface area of Russia, actually. And Russia is big, but it's not a planet. Well, I mean, actually, we can touch more on that.
That's another discussion. So in some sense, earlier in the century, Pluto represented kind of our ignorance about the edges of the solar system. And perhaps Planet 9 is the thing that represents our ignorance about now, the modern set of ignorances about the edges of our solar system.
That's a good way to put it.
By the way, just imagining this belt of debris at the edge of our solar system is incredible.
Yeah.
Can you talk about it a little bit? What is the Kuiper Belt, and what is the Oort cloud?
Yeah. Okay. So look, the simple way to think about it is that if you imagine, Neptune's orbit like a circle, right? Kind of maybe a factor of 1.3 times bigger on a radius of 1.3 times bigger. You've got a whole collection of icy objects. Most of these objects are sort of the size of Austin, maybe a little bit smaller. If you then zoom out, right, and explore the orbits of the most long period Kuiper Belt objects, these are the things that have the biggest orbits and take the longest time to go around the sun, then what you find is that beyond a critical orbit size, beyond a critical orbit period, which is about 4,000 years, you start to see weird structure. Like all the orbits sort of point into one direction. And all the orbits are kind of tilted in the same way by about 20 degrees with respect to the sun. This is particularly pronounced in orbits that are not heavily affected by Neptune. So there you start to see this weird dichotomy where there are objects which are stable, which Neptune does not mess with gravitationally, and unstable objects. The unstable objects are basically all over the place because they're being, kicked around by Neptune. The stable orbits show this remarkable pattern of clustering. We, back, I guess, 5 years ago, interpreted this pattern of clustering as a gravitational one-way sign of the existence of a planet in a distant planet, right? Something that is shepherding and confining these orbits together. Of course, right, you have to have some skepticism when you're talking about these things. You have to ask the question of, okay, how statistically significant is this clustering? And there are many authors that have indeed called that into question. We have done our own analyses, and basically, just like with all statistics, where there's kind of like multiple ways to do the exercise. Mm-hmm. You can either ask the question of, if I have a telescope that has surveyed this part of the sky, what are the chances that I would discover this clustering? And that basically tells you that you have zero confidence, right? Like that does not give you a confident answer one way or another. Another way to do the statistics, which is what we prefer to do, is to say we have a whole night sky of discoveries in the Kuiper Belt, right? And if we have some object over there, which has right ascension and declination, which is a way to say it's there on the sky, and it has some brightness, that means somebody looked over there and was able to discover an object of that brightness or brighter. And through that analysis, you can construct a whole map on the sky of kind of where all of the surveys that have ever been done have collectively looked. So if you do the exercise this way, the false alarm probability of the clustering on which the Planet 9 hypothesis is built is about 0.4%.
Wow. Okay, so there's a million questions here. One, when you say bright objects, why are they bright? Are we talking about actual objects within the Kuiper Belt or the stuff we see through the Kuiper Belt?
This is the actual stuff we see in the Kuiper Belt. The way you go about discovering Kuiper Belt objects is pretty easy. I mean, it's easy in theory, right? Hard in practice.
Yeah.
All you do is you take snapshots of the sky, right? Choose that direction, say, and take, the high exposure snapshot. Mm-hmm. Then you wait a night and you do it again. And then you wait another night and you do it again. Objects that are just random stars in the galaxy don't move on the sky, whereas objects in the solar system will slowly move. This is no different than if you're driving down the freeway, it looks like, trees are going by you faster than the clouds, right? Mm-hmm. This is parallax. That's it. It's just they're reflecting light off of the sun and it's going back and hitting this.
There's a little bit of a glimmer from the different objects that you can see based on the reflection from the sun. So like there's actual light. Yep. So it's not darkness.
That's right. These are just big icicles, basically, that are just reflecting sunlight back at you. It's then easy to understand why it's so hard to discover them, because light has to travel to, something like 40 times the distance between the Earth and the sun and then get reflected back.
Was that like an hour travel? Or
yeah, that's right. That's something like that, because the Earth to the sun is 8 minutes, I believe, and so
something,
hours.
in that order of magnitude. So that's interesting. So you have to like account for all of that, and then there's this huge amount of data, pixels that are coming from the pictures, and you have to integrate all of that together to paint a sort of like a high estimate of the different objects. Can you track them? Can you be like, that's Bob? Like, can you like?
Yes, exactly. In fact, one of them is named Joe Biden. Right? I mean, I'm not like, this is not even a joke. Right.
Okay. Is there a Trump one or no?
No. I don't, well,
not
actually,
yet.
I don't know. I haven't checked for that, but like the way it works is if you discover one, you right away get a license plate for it. Okay. So like the first 4 numbers is the first year that this object has appeared on, in the data set, if you will. And then there's like this code that follows it, which basically tells you where in the sky it is, right? So one of the really interesting Kuiper Belt objects, which is very much part of the Planet 9 story, is called VP113. Because Joe Biden was vice president at the time, got nicknamed Biden.
VP 113, you said?
Yeah.
He got nicknamed Biden. Beautiful. What's the fingerprint for any particular object? Like, how do you know it's the same one? Okay. Or you just kind of like, from night to night, you take a picture. How do you know it's the same object?
Yeah, so the way you know is it appears in almost exactly the same part of the sky, except for moves by. And this is why actually you need at least 3 nights, because oftentimes asteroids, which are much closer to the Earth, like will appear to move only slightly, but then on the 3rd night will move away. So that 3rd night is really there to detect acceleration. Now, the thing that I didn't really realize until, I started observing together with my partner in crime and all this, Mike Brown, is just the fact that for the first year when you make these detections, the only thing you really know with confidence is where it is on the night sky and how far away it is. Mm-hmm. Okay? That's it. You don't know anything about the orbit, because over 3 days, the object just moves so little. Right? That whole motion on the sky is entirely coming from motion of the Earth, right? So the Earth is kind of the car, the object is the tree, and you see it move. Yeah. So then to get some confident information about what its orbit looks like, you have to come back a year later and then measure it again.
Oh, interesting. So do 3 nights, then come back a year later and do another 3 nights.
Yeah.
So you get the velocity, the acceleration from the 3 nights, and then you have the maybe
the additional
information.
Because an orbit is basically described by 6 parameters. So you at least need 6 independent points, but in reality, you need many more observations to really pin down the orbit well.
And from that, you're able to construct for that one particular object an orbit. And then there's, of course, like how many objects are there?
There's like 4-ish thousand now.
But like in the future, there could be like millions.
Oh, sure.
So
in fact, these things are hard to predict, but there's a new observatory called the Vera Rubin Observatory, which is coming online maybe next year. I mean, with COVID, these things are a little bit more uncertain, but they've actually been making great progress with construction. And so that telescope is just going to sort of scan the night sky every day automatically. And it's such an efficient survey that it might increase the census of the distant Kuiper Belt, the things that I'm interested in, by a factor of 100. I mean, that would be really cool.
And that's an incredible.
They might just find Planet 9. Too. I mean, that's
like almost like literally pictures, like visually.
I mean, sure, yeah. Like the first detection you make, all you know is where it is in the sky and how far away it is. If something is, 500 times away from the sun, as far away from the sun as is the Earth, that's Planet 9. That's when the story concludes. And then you can study it.
Now you can study it, yeah. By the way, I'm going to use that as like, I don't know, a pickup line or a dating strategy. Like see the person for 3 days and then don't see them at all and then see them again in a year to determine the orbit. And over time, you figure out if sort of from a cosmic perspective, this whole thing works out.
I have no dating advice to give.
I was gonna use this as a metaphor to somehow to map it onto the human condition. Okay, you mentioned the Kuiper Belt. What's the Oort cloud? If you look at the Neptune orbit as 1, then the Kuiper Belt is like 1.3 out there, and then we get farther and farther into the darkness. Right.
You've got the kind of main Kuiper Belt, which is about say 1.3, 1.5. Then you have something called the scattered disk, which is kind of an extension of the Kuiper Belt. It's a bunch of these long, very elliptical orbits that hug the orbit of Neptune but come out very far. So that the scattered disk, with the current census, like some of the longest orbits we know of, have a semi-major axis, so half the orbit length, roughly speaking, of about 1,000 times the distance between the Earth and the Sun.
Wow.
Now, if you keep moving out, eventually, once you're at sort of 10,000 to 100,000 roughly, that's where the Oort cloud is. Now, the Oort cloud is a distinct population of icy bodies and is distinct from the Kuiper Belt. In fact, it's so expansive that it ends roughly halfway between us and the next star. Its edge is just dictated by to what extent does the solar gravity reach.
Solar gravity reaches that far?
Yeah.
So it has to, wow.
Yeah. So, in fact,
imagining this is a little bit overwhelming. So there's like a giant, like vast, icy rock thingy.
It's like a sphere. It's like, it's an almost spherical structure that encircles the sun. And all the long period comets come from the Oort cloud. They come, the way that they appear, for already, hundreds of years, we've been detecting it occasionally, like a comet will come in and it seemingly comes out of nowhere.
Yeah.
The reason these long period comets appear that on very, very long time scales, right? These Oort cloud objects that are sitting, 30,000 times as far away from the sun as is the Earth, actually interact with the gravity of the galaxy, effectively the tide that the galaxy exerts upon them, and their orbits slowly change and they elongate to the point where once their closest approach to the sun starts to reach a critical distance where ice starts to sublimate, then we discover them as comets because then the ice comes off of them. Wow. They look beautiful on the night sky, etc. But they're all coming from, really, really far away.
So are any of them coming our way from collisions? Like, how many collisions are there? Or is there a bunch of space for them to move around?
Yeah, there's zero. It's completely collisionless. Out there, the physical radii of objects are so small compared to the distance between them, right? It is truly a collisionless environment. I don't know. I think that probably in the age of the solar system, there have literally been zero collisions in the Oort cloud.
Wow. When you draw a picture of the solar system, everything's really close together. So that everything, I guess, here is spaced far apart. Do rogue planets fly in every once in a while and join? Not rogue planets, but rogue objects from out there.
Oh, sure. Yeah.
Join the party?
Yeah, absolutely. We've seen a couple of them in the last 3 or so years, maybe 4 years now. The first one was the one called Oumuamua, and it's been all over the news. The second one was Comet Borisov, discovered by a guy named Borisov. Yeah, so the way you know they're coming from elsewhere is, unlike solar system objects, which travel on elliptical paths around the sun, these guys travel on hyperbolic paths. Mm-hmm. So they come in, say hello, and then they're gone. And the fact that they exist is totally not surprising, right? Mm-hmm. The Neptune is constantly ejecting Kuiper Belt objects into interstellar space. Our solar system itself is sort of leaking icy debris and ejecting it. So presumably every planetary systems around other stars do exactly the same thing.
Let me ask you about the millions of objects that are part of the Kuiper Belt and the part of the Oort cloud. Do you think some of them have primitive life? It kind of makes you sad. If there's primitive life there and they're just kind of lonely out there in space. Yeah. How many of them do you think have life, bacterial life?
Probably a negligible amount. Zero, zero with a plus on top.
Right.
Right.
Zero plus.
Yeah. If you and I took a little trip to the interstellar medium, I think we would develop cancer and die real fast, right?
It's rough.
Yeah, it's a pretty hostile radiation environment. You don't actually have to go to the interstellar medium. You just have to leave the Earth's magnetic field and then you're not doing so well suddenly. So, yeah. This idea of, life kind of traveling between places, it's not entirely implausible, but you really have to twist, I think, a lot of parameters. One of the problems we have is we don't actually know how life originates, right? So it's kind of a second order question of survival in the interstellar medium and how resilient it is, because we think you require water, and that's certainly the case for the Earth, but we really don't know for sure. That said, I will argue that the question of are there aliens out there is a very boring question, because the answer is, of course there are. Right? I mean, we know that there are planets around almost every star. Of course there are other life forms. Life is not some specific thing that happened on the Earth and that's it, right? Just that's a statistical impossibility.
Yeah. Yeah, but the difficult question is, before even the fact that we don't know how life originates, I don't think we even know what life is, definitionally.
Yeah.
Formalizing a kind of picture of, in terms of the mechanism we would use to search for life out there, or even when we're on a planet, to say, is this life? Is this rock that just moved from where it was yesterday life? Or maybe not even a rock, something else.
I got to tell you, I want to know what life is. Okay. And I want you to show me.
Uh, I think there's a song to basically accompany every single thing we talk about today, and probably half of them are love songs. And somehow we'll integrate George Michael into the whole thing. Okay, so your intuition is there's life everywhere in our universe. Do you think there's intelligent life out there?
I think it's entirely plausible. I mean, it's entirely plausible. I think there's intelligent life on Earth, and
so yeah, taking that, like, say whatever this thing we got on Earth, whether it's dolphins or humans, say that's intelligent.
Definitely dolphins. I mean, have you seen the dolphins?
Well, they do some cruel stuff to each other. So if cruelty is a definition of intelligence, they're pretty good.
Yeah.
And then humans are pretty good on that regard. And then there's like pigs are very intelligent. I got actually a chance to hang out with pigs recently, and they're aside from the fact they're trying to eat me, they're very they love food. They love food, but there's an intelligence to their eyes that was kind of like haunts me, because I also love to eat meat, and then to meet the thing I later ate, and that was very intelligent and almost charismatic with the way it was expressing himself, herself, itself, was quite incredible. So all that to say is, if we have intelligent life here on Earth, if we take dolphins, pigs, humans, from the perspective of like planetary science, how unique is Earth?
Okay, so Earth is not a common outcome of the planet formation process. It's probably something on the order of maybe a 1% effect. And by Earth, I mean not just an Earth mass planet. Okay, I mean the architecture of the solar system that allows the Earth to exist in its kind of very temperate way. One thing to understand, and this is pretty crucial, right, is that the Earth itself formed well after the gas disk that formed the giant planets had already dissipated. You see, stars start out with, the star and then a disk of gas and dust that encircles it. Okay, from this disk of gas and dust, big planets can emerge, and we have over the last 2-3 decades discovered thousands of extrasolar planets, planets in orbit of other stars. What we see is that many of them are have these expansive hydrogen helium atmospheres. The fact that the Earth doesn't is deeply connected to the fact that Earth took about 100 million years to form. So we missed that train, so to speak, to get that hydrogen helium atmosphere. That's why actually we can see the sky, right? That's why the sky is, at least in most places, that's why the atmosphere is not completely opaque. With that, kind of thinking in mind, I would argue that we're getting the kind of emergent pictures that the Earth is not, everywhere, right? There's sort of the sci-fi view of things where we go to some other star and we just land on random planets and they're all Earth-like. That's totally not true. But even a low probability event, even if you imagine that Earth is a 1 in a million or 1 in 10 million occurrence, there are 10 to the 12 stars in the galaxy. Right, so you always win by
large numbers.
That's right, by supply.
They save you. Well, you've hypothesized that our solar system once possessed a population of short period planets that were destroyed by the evil Jupiter, migrating through the solar nebula. Can you explain?
If I was to say what was the key outcome of searches for extrasolar planets, it is that most stars are encircled by short period planets that are, a few Earth masses, right? So a few times bigger than the Earth, and have orbital periods that kind of range from days to weeks. Okay?
Oh, wow.
Now, if you go and ask the solar system what's in our region, right? in that region. It's completely empty, right? It's astonishingly hollow. And I think, from the sun is not some, special star that decided that it was going to form the solar system. So I think, the natural thing to assume is that the same processes of planet formation that occurred everywhere else also occurred in the solar system. Following this logic, it's not implausible to imagine that the solar system once possessed a system of intra-Mercurian, compact system of planets. So then we asked ourselves, would such a system survive to this day? And the answer is no. At least our calculations suggest that it's highly unlikely because of the formation of Jupiter. And Jupiter's primordial kind of wandering through the solar system would have sent this collisional field of debris that would have pushed that system of planets onto the sun.
So was Jupiter, this primordial wandering, what did Jupiter look like? Why was it wandering? It didn't have the orbit it has today?
We're pretty certain that giant planets like Jupiter, when they form, they migrate. The reason they migrate is, on a detailed level, perhaps difficult to explain, but just in a qualitative sense, they form in this fluid disk of gas and dust. So it's kind of like saying, okay, if I plop down a raft somewhere in the ocean, will it stay where you plop it down, or will it kind of get carried around? It's not really a good analogy because it's not like Jupiter is being advected by the currents of gas and dust, but the way it migrates is it carves out a hole in the disk, and then by interacting with the disk gravitationally, right, it can change its orbit. The fact that the solar system has both Jupiter and Saturn here complicates things a lot, right? Because you have to solve the problem of the evolution of the gas disk, the evolution of Jupiter's orbit in the gas disk, plus the evolution of Saturn's and their mutual interaction. The common outcome of solving that problem, though, is pretty easy to explain. Jupiter forms, its orbit shrinks, and then once Saturn forms, its orbit catches up basically to the orbit of Jupiter, and then both come out. So there's this inward-outward pattern of Jupiter's early motion that happens sort of within the last million years of the lifetime of the solar system's primordial disk. So while this is happening, if our calculations are correct, which I think they are, you can destroy this inner system of few Earth mass planets. And then in the aftermath of all this violence, you form the terrestrial planets.
Where would they come from in that case? So Jupiter clears out the space, and then there's a few terrestrial planets that come in, and those come in from the disk somewhere, so one of the larger objects?
What actually happens in these calculations is you leave behind a rather mass-depleted, remnant disk, only a couple Earth masses. Yeah. So then from that remnant population, annulus of material over about 100 million years, by just collisions, you grow the Earth and the Moon and everything else.
You said annulus?
Annulus.
Annulus,
yeah.
That's a beautiful word. What does that mean?
Well, it's like a disc that's kind of thin. It's it's something that is, a disc that's so thin it's almost flirting with being a ring.
Like, I was gonna say, this reminds me of Lord of the Rings. So the word just feels like it belongs in a Tolkien novel. Yeah. Okay. So that's incredible. And so that, in your senses, you said 1%, that's a rare. The way Jupiter and Saturn danced and cleared out and cleared out the short period debris and then changed the gravitational landscape. That's a pretty rare thing to.
It's rare, and moreover, you don't even have to go to our calculations. You can just ask the night sky, how many stars have Jupiter and Saturn analogs? And the answer is Jupiter and Saturn analogs are found around only 10% of sun-like stars. So they themselves, you kind of have to score an A- or better on the test on the planet formation test to become a solar system analog, even in that basic sense. And moreover, lower mass stars, which are very numerous in the galaxy, so-called M dwarfs, think like 0% of them, well, maybe like some negligible fraction of them have giant planets. Giant planets are a rare, outcome of planet formation. One of the really big problems that remain unanswered is why. We don't actually understand why they're so rare.
How hard is it to simulate all of the things that we've been talking about, each of the things we've been talking about, and maybe one day all of the things we've been talking about and beyond? Meaning, like from the initial primordial solar system, a bunch of disks with, I don't know, billions, trillions of objects in them, like simulate that such that you eventually get a Jupiter and a Saturn, and then eventually you get the Jupiter and the Saturn that clear out a disk, change the gravitational landscape, then Earth pops up, like that whole thing, and then be able to do that for every other system in the every other star in the galaxy, and then be able to do that for other galaxies as well.
Yeah. So look,
maybe start from the smallest simulation, like what is actually being done today. I mean, even the smallest simulation is probably super, super difficult. Even just like one object in the Kuiper Belt is probably super difficult to simulate.
I mean, I think it's super easy. I mean, like it's it's just not that hard. But let's ask the most kind of basic problem. Okay, so the problem of having a star and something in orbit of it that you don't need a simulation for. Like you can just write that down on a piece of paper.
Mm-hmm. There's gravity. I guess it's important to try to, one way to simulate objects in our solar system is to build the universe from scratch.
Okay, we'll get to building the universe from scratch in a sec. But let me just kind of go through the hierarchy of what we do.
Two objects.
Right, so two objects, analytically solvable. Like we can figure it out very easily if you don't need to know calculus. It helps to know calculus, but you don't necessarily need to know calculus. Three objects that are gravitationally interacting, the solution is chaotic. Doesn't matter how many simulations you do, the answer loses meaning after some time.
I feel like that is a metaphor for dating as well, but go on.
Now look, so the fact that you go from analytically solvable to unpredictable, when your simulation goes from two bodies to three bodies, should immediately tell you that the exercise of trying to engineer a calculation where you form the entire solar system from scratch and hope to have some predictive answer is a futile one, right? We will never succeed at such a simulation.
So, sorry, just to clarify, you mean like explicitly having a clear equation that generalizes the whole process enough to be able to make a prediction? Or do you mean actually like literally simulating the objects is a hopeless pursuit once it increases beyond three?
The simulating them is not a hopeless pursuit, but the outcome becomes a statistical one. Right. And what's actually quite interesting is I think we have all the equations figured out, right? In order to really understand this, the formation of the solar system, it suffices to know gravity and magnetohydrodynamics. I mean, like the combination of Maxwell's equations and Navier-Stokes equations for the fluids. You need to know quantum mechanics to understand opacities and so on. But we have those equations in hand. It's not that we don't have that understanding. It's that putting it all together is A, very, very difficult, and B, if you were to run the same evolution twice, changing, the initial conditions by some infinitesimal amount, some, minor change in your calculation to start with, you'd get a different answer. This is part of the reason why planetary systems are so diverse. You don't have like a very predictive path for you start with a disk of this mass and it's around this star, therefore you're going to form the solar system, right? you start with this, and therefore you will form this huge outcome, a huge set of outcomes, and some percentage of it will resemble the solar system.
You mentioned quantum mechanics, and we're talking about cosmic scale objects. You've talked about that the evolution of astrophysical disks can be modeled with Schrodinger's equation.
I sure did.
Why? It's like, how does quantum mechanics become relevant when you consider the evolution of objects in the solar system?
Yeah. Well, let me take a step back and just say it. Like, I remember being, utterly confused by quantum mechanics when I first learned it. And the Schrodinger equation, which is kind of the parent equation of that whole field, seems to come out of nowhere, right? The way that I was sort of explaining it, I remember asking, my professor, I was like, but where does it come from? He's like, well, just like, don't worry about it, and just like calculate the hydrogen, energy levels, right? So it's like I could do all the problems. I just did not have any intuition for where this parent, super important equation came from. Now, down the line, I was preparing for my own lecture, and I was trying to understand how waves travel in self-gravitating disks. So, again, there's a very broad theory that's already developed, but I was looking for some simpler way to explain it, really, for the purposes of teaching class. And so I thought, okay, what if I just imagine a disk as an infinite number of concentric circles, right, that interact with each other gravitationally? That's a problem in some sense that I can solve using methods from like the late 1700s. Right? So I can write down Hamiltonian. Well, I can write down the energy function basically of their interactions. And what I found is that when you take the continuum limit, when you go from discrete circles that are talking to each other gravitationally to a continuum disk, suddenly this gravitational interaction among them, right, the governing equation becomes the Schrodinger equation. Yeah. And I had to think about that for a little bit.
Did you just unify quantum mechanics and gravity?
No, this is not the same thing as like, fusing relativity and quantum mechanics. But it did get me thinking a little bit. So the fact that waves in astrophysical disks behave just like wave functions of particles, kind of like an interesting analogy, because for me it's easier to imagine waves traveling through, astrophysical disks, or really just sheets of paper. And the reason this is that analogy exists is because there's actually nothing quantum about the Schrodinger equation. The Schrodinger equation is just a wave equation, and all of the interpretation that comes from it is quantum, but the equation itself is not a quantum being.
So you can use it to model waves. It's It's not turtles. It's waves all the way down. You can pick which level you pick the wave at, and so it could be at the solar system level that you can use.
Right, and also it actually provides a pretty neat calculational tool, because it's difficult. So we just talked about simulations, but it's difficult to simulate the behavior of astrophysical disks on timescales that are in between a few orbits and their entire evolution. So it's over a timescale of a few orbits. You do a hydrodynamic, simulation, right? You do that. Basically, that's something that you can do on a modern computer on a timescale of, say, a week. When it comes to their evolution over their entire lifetime, you don't hope to resolve the orbits. You just kind of hope to understand how the system behaves. In between, right? To get access to that, as it turns out, it's pretty cute. You can use the Schrodinger equation to get the answer rapidly. So it's a calculational tool.
That's fascinating. By the way, astrophysical disks, what are they? How broad is this definition?
Okay, so astrophysical disks span a huge amount of ranges. They start maybe at the smallest scale. They start with actually Kuiper Belt objects. Some Kuiper Belt objects have rings, Okay? So that's maybe the smallest example of an astrophysical disk. We've got this little potato-shaped asteroid, which is, sort of the size of LA or something, and around it are some rings of icy matter. That object is a small astrophysical disk. Then you have Saturn, the rings of Saturn. You have the next set of scale. You have the solar system itself when it was forming. You have a disk. Then you have black hole disks. You have galaxies. Disks are super common in the universe. And the reason is that stuff rotates. Right. I mean,
gravity works.
Yeah.
So, and those rings could be the material that composes those rings. It could be gas. It could be solid. It could be anything.
That's right. So, the disk from which the planets emerged was predominantly hydrogen and helium gas. On the other hand, the rings of Saturn are made up of little like ice cubes this big, about a centimeter across.
That sounds refreshing. So that's incredible. Hydrogen and helium gas. So in the beginning, it was just hydrogen and helium around the sun. How does that lead to the first formations of solid objects in terms of simulation?
Okay, here's the story. So have you ever been to the desert?
Yes, I've been to the Death Valley, and actually it was terrifying. Just a total tangent. I'm distracting you.
No problem.
But I was driving through it, and I was really surprised because it was at first hot, and then as it was getting into the evening, there's this huge thunderstorm. It was raining, and it got freezing cold. I was like, what the hell? It was the apocalypse.
Yes.
I had to just sit there listening to Bruce Springsteen, I remember, and just thinking, I'm probably going to die. And I was okay with it, because Bruce Springsteen was on the radio.
Look, when you've got the boss, you're ready. You're ready to meet the boss. Yeah. So look, I mean,
it's a good line.
So
anyway, sorry.
It's true. Yeah. By the way, to continue on this tangent, I absolutely love the Southwest for this reason. Just during the pandemic, I drove from LA to New Mexico a bunch of times.
The madness of weather.
Yeah, the chaos of weather, the fact that, it'll be blazing hot one minute and then it's just like we'll decide to have a little thunderstorm. Maybe we'll decide to go back momentarily to 1,000 degrees and then go back to the thunderstorm. It's amazing. It's that, by the way, is chaos theory in action.
Yeah.
Right. But let's get back to talking about the desert.
Yeah.
So in the desert, tumbleweeds have a tendency to roll because the wind rolls them. And if you're careful, you'll occasionally see this family of tumbleweeds where there's a big one and then a bunch of little ones that kind of hide in its wake, right? And are all rolling together and it almost looks like, a family of ducks crossing a street or something. Or, for example, if you watch Tour de France, right, you've got a whole bunch of cyclists and they're cycling, within 10 centimeters of each other. They're not BFFs, right? Yeah. They're not trying to be trying to ride together. Yeah. They are riding together to minimize the collective, air resistance, if you will, that they experience. Turns out solids in the protoplanetary disk do just this. There's an instability wherein solid particles, right, things that are a centimeter across, will start to hide behind one another and form these clouds. Why? Because cumulatively, that minimizes the solid component of the disk aerodynamic interaction with the gas. Now, these clouds, because they're kind of a favorable energetic condition for the dust to live in, they grow until they become so massive that they collapse under their own weight. That's how the first building blocks of planets form. That's how the big asteroids got there.
That's incredible.
Yeah.
So is that simulatable, or is it not useful to simulate?
No, that's simulatable. And people do these types of calculations. It's really cool. That's one of the many fields of planet formation theory that is really, really active right now. People are trying to understand all kinds of aspects of that process because, of course, I've explained it, as if there's one thing that happens. Turns out it's a beautifully rich dynamic, but qualitatively, formation of the first building blocks actually follows the same sequence as formation of stars, right? Stars are just clouds of gas, hydrogen, helium gas that sit in space and slowly cool. And at some point they, contract to a point where their gravity overtakes the thermal, pressure support, if you will, and they collapse under their own weight. And you get a little baby solar system.
That's amazing. So do you think one day it'll be possible to simulate the full history that took our solar system to what it is today?
Yes, and it will be useless. Okay.
So you don't think your story, many of the ideas that you have about Jupiter, clearing the space, like retelling that story in high resolution is not that important?
I actually think it's important, but at every stage, you have to simulate, you have to design your experiments, your numerical computer experiments, so that they test some specific aspect of that evolution.
Got it.
I am not a proponent of doing huge simulations because even if we forget the information theory aspect of not being able to simulate in full detail the universe, because if you do, then you have made an actual universe. It's not the simulation, right? By simulation is in some sense a compression of information, so therefore you must lose detail. But that point aside, if we are able to simulate the entire history of the solar system in excruciating detail, I mean, it'll be cool, but it's not going to be any different from observing it, right? Because theoretical understanding, which is what ultimately I'm interested in, comes from taking complex things and reducing them down to something that, some mechanism that you can actually quantify. That's the fun part of astrophysics. Just kind of simulating things in extreme detail will make cool visualizations, but that doesn't get you to any better understanding than you had before you did the simulation.
If you ask very specific questions, then you'll be able to create like very highly compressed, nice, beautiful theories about how things evolved, and then you can use those to then generalize to other solar systems, to other stars and other galaxies, and then say something generalizable about the entire universe. How difficult would it be to simulate our solar system such that we would not know the difference? Meaning, if we are living in a simulation, is there a nice, think of it as a video game,
sure.
Is there a nice compressible way of doing that? Or just kind of like you intuited with a 3-body situation, is just a giant mess that you cannot create a video game that will seem realistic without actually building a universe from scratch?
I'm speculating, but one of the, I know, you have a deep understanding of this, but for me, I'm just going to speculate that for at least in the types of simulations that we can do today, inevitably you run into the problem of resolution, right? Doesn't matter what you're doing, it is discrete. Now, the way you would go about asking, if what we're observing, is that a simulation or is that, some real continuous thing, is you zoom in, right? You zoom in and try and find the grid scale, if you will. I mean, it's a really interesting question, and because the solar system itself and really, the double pendulum is chaotic, right? Pendulum sitting on another pendulum, it moves unpredictably once you let them go. You really don't need to inject any randomness into a simulation for it to give you stochastic and unpredictable answers. Weather is a great example of this. Weather has a lapse of time of, typical weather systems have a lapse of time of a few days. And there's a fundamental reason why the forecast always sucks, 2 weeks in advance. It's not that we don't know the equations that govern the atmosphere. We know them well. Their solutions are meaningless, though, after a few days.
The zooming in thing is very interesting. I think about this a lot, whether there'll be a time soon where we would want to stay in video game worlds, whether it's virtual reality or just playing video games.
I mean, I think that time like came in like the 90s, and it's been that time.
Well, it's not just game. It's accelerated. I just recently saw that WoW and Fortnite were played 140 billion hours, and those are just video games.
Yeah.
And that's like increasing very, very quickly, especially with the people coming up now, being born now, and becoming teenagers, and so on. Let's have a thought experiment where it's just you and a video game character inside a room, where you remove the simulation, the need to simulate sort of a lot of objects. If it's just you and that character, how far do you need to simulate in terms of zooming in for it to be very real to you? As real as reality. So like, first of all, you kind of mentioned zooming in, which is fascinating because we have these tools of science that allow us to zoom in, quote unquote, in all kinds of ways in the world around us. But our cognitive abilities, like our perception system as humans, is very limited in terms of zooming in. So we might be very easily fooled.
Some of the video games, like on the PS4, like look pretty real to me, right? I think you would really have to interrogate. I think even with what we have today, like I don't know, Ace Combat 7 is a great example, right? Like, I mean, the way that the clouds are rendered, it looks just like when you're flying, on a real airplane. The kind of transparency. I think that our perception is limited enough already to not be able to tell some of the differences.
There's a game called Skyrim. It's an Elder Scrolls role-playing game, and I played it for quite a bit, and I think I played it very different than others. Like there'll be long stretches of time where I would just walk around and look at nature in the game. It's incredible.
Oh, sure.
It's just like the graphics is like, wow, I want to stay there. It was better. I went hiking recently. It was like as good as hiking.
So look, I know what you mean. Not to go on a huge video game, tangent, but like the third like Witcher game was astonishingly beautiful, right? Especially like playing on a good hardware machine. It's like this is pretty legit. That said, I don't resonate with the I want to stay here. Like one of the things that I love to do is to go to my like boxing gym and box with a guy, right? Like there's nothing quite like that physical, experience. Like
that's fascinating. That might be simply an artifact of the year you were born.
Maybe.
Because if you're born today, it almost seems like stupid to go to a gym.
Yeah.
Like you're going to a gym to box with a guy. Why not box with Mike Tyson when you yourself is like in his prime, when you yourself are also an incredible boxer in the video game world?
For me, there's a multitude of reasons why I don't want to box with Mike Tyson, right? Like,
No.
I enjoy teeth, and I want to have an ear.
No, but your skills in this meat space, in this physical realm, is very limited, and it takes a lot of work. And you're a musician, you're an incredible scientist. You only have so much time in the day, but in the video game world, you can expand your capabilities in all kinds of dimensions that you can never possibly have time in the physical world. And so that it doesn't make sense, like to be working your ass off in the physical world when you can just be super successful in the video game world.
But you
enjoy sucking and stuff?
Yeah, I really
and struggling to get better.
I sure do. I mean, I think like these days with music is a great example, right? We just started, practicing live with my band again, after not playing for a year. And, it was terrible. Like it was just kind of a lot of the nuance, a lot of the detail is just that detail that takes, years of collective practice to develop is just lost. But it was an incredible amount of fun, way more fun than all the like studio, sitting around and playing that I did, throughout the entire year. So I think there's something intangible, or maybe tangible, about being in person. I sure hope you're wrong, and that that's not something that will get lost, because I think there's like such a large part of the human condition is to hang out. If we were doing this interview on Zoom, right? I mean, I'd already be bored out of my mind.
Exactly. I mean, there's something to that. I'm almost playing devil's advocate, but at the same time, I'm sure people talk about the same way at the beginning of the 20th century about horses, where they are much more efficient. They're much easier to maintain than cars. It doesn't make sense to have, all the ways that cars break down, and there's not enough infrastructure in terms of roads for cars. It doesn't make any sense. Like horses, totally, and like nature, you could do the nature, like where, you should be living more natural life. Those are real. You don't want machines in your life. They're going to pollute your mind and the minds of young people. But then eventually just cars took over. So in that same way, it just seems...
going back to horses. After I'm just,
Well, you can play, what is it? Red Dead
Redemption. Yeah.
Redemption, and you can ride horses in the video game world.
That's true.
So let me return us back to Planet Nine.
Always a good place to come back to.
So now that we did a big historical overview of our solar system, what is Planet Nine?
Okay. Planet Nine is a hypothetical object that orbits the solar system, right, at an orbital period of about 10,000 years. And an orbit which is slightly tilted with respect to the plane of the solar system, slightly eccentric. And the object itself, we think, is 5 times more massive than the Earth. We have never seen Planet 9 in a telescope, but we have gravitational evidence for it.
And so this is where all the stuff we've been talking about, this clustering ideas, maybe you can speak to the approximate location that we suspect. And also the question I wanted to ask is, what are we supposed to be imagining here? Because you said there's certain objects in the Kuiper Belt that are kind of have a direction to them, that they're all like flocking in some kind of way. Mm-hmm. So that's a sense that there's some kind of gravitational object, not changing their orbit, but kind of
confining them, right? Like grouping their orbits together. See, what would happen if Planet 9 were not there is these orbits that roughly share a common orientation, they would just disperse, right? They would just become azimuthally symmetric, point everywhere. Planet 9's gravity makes it such that these objects stay in a state that's basically anti-aligned with respect to the orbit of Planet 9, and sort of hang out there and kind of oscillate on a timescale of about 1 billion years. That's one of the lines of evidence for the existence of Planet 9. There are others. That's the one that's easiest to maybe visualize, just because it's fun to think about orbits that all point into the same direction. But I should emphasize that, for example, the existence of objects, again, Kuiper Belt objects, that are heavily out of the plane of the solar system, things that are tilted by, say, 90 degrees, that's not, we don't expect that as an outcome of planet formation. Indeed, planet formation simulations have never produced such objects without some extrinsic gravitational force. Mm-hmm. Planet 9, on the other hand, generates them very readily. So that provides kind of an alternative, population of small bodies in the solar system that also get produced by Planet 9 through an independent kind of gravitational effect. So there's basically 5 different things that that Planet 9 does individually that are like kind of maybe a 1 sigma effect, where you'd say, yeah, okay, if that's all it was, maybe it's no reason to jump up and down. But because it's a multitude of these puzzles that all are explained by one hypothesis, that's really the magnetism, the attraction of the Planet 9 model.
So can you just clarify?
Mm-hmm.
So most planets in the solar system orbit and approximately the same, so
That's
it's flat.
Yeah, it's like 1 degree. The difference between them is about 1 degree.
So, but nevertheless, if we looked at our solar system, it would look, and like could see every single object, it would look like a sphere.
The inner part where the planets are would look like flat, right? The Kuiper Belt and the asteroid belt have a larger.
So it gets fatter and fatter and
it's
fatter
kind of
until
like
it becomes a sphere.
That's right. And if you look at the very outside, it's polluted by this, quasi-spheroidal thing. Nobody's, of course, ever seen the Oort cloud, right? We've only seen comets that come from the Oort cloud. So the Oort cloud, which is this, right, population of distant debris, its existence is also inferred. You could say, alternatively, there's a big cosmic creature that occasionally, sitting at 20,000 AU and occasionally throws an icy rock towards the sun. Like that.
Spaghetti monster, I think it's called. Okay. Yeah. I mean, so it's a mystery in many ways, but you can kind of infer a bunch of things about it. It's, by the way, both terrifying and exciting that there's this vast darkness all around us that's full of objects that are just throwing.
They're just there. Yeah. It's actually kind of astonishing, right? That we have only explored a small fraction of the solar system, right? That really kind of baffles me because remember as a student, studying physics, you do the problem where you put the Earth around the sun, you solve that, and like it's one line of math, and you say, okay, well that surely was figured out by Newton. Yeah. So like all the interesting stuff is not in the solar system, but that it's just plainly not true. There are mysteries in the solar system that are remarkable that we are only now starting to just kind of scratch the surface of.
And some of those objects probably have some information about the history of our solar system.
Absolutely. Like a great example is, small meteorites, right? Small meteorites are melted, right? They're differentiated, meaning some of the iron sinks to core. You say, well, how can that be? Because they're so small that they wouldn't have melted just from the heat of their accretion. Mm-hmm. Turns out the fact that the solar nebula, the disk that made the planets, was polluted by aluminum-26 is in itself a remarkable thing. It means the solar system did not form in isolation. It formed in a giant cloud of thousands of other stars that were also forming, some of which were undergoing, going through supernova explosions, and releasing these unstable isotopes of which we now see kind of the traces of. It's so cool.
Do you think it's possible that life from other solar systems was injected, and that was what was the origin of life on Earth?
Yeah, the panspermia idea.
That's seen as a low probability event by people who studied the origin of life, but that's because then they would be out of a job.
Well, I don't think they'd be out of the job because you just then you have to figure out how life started there.
But then you have to go there. We can study life on Earth much easier. We could study it in the lab much easier because we can replicate conditions that are from an early Earth much easier. From a chemistry perspective, from a biology perspective, you can intuit a bunch of stuff. You can look at different parts of Earth and just...
To an extent, I mean, the early Earth was completely unlike the current Earth, right? Yeah. There was no oxygen. So one of my colleagues at Caltech, Joe Kirschnick, is certain, right, with something like 100% certainty that life started on Mars and came to Earth on Martian meteorites. This is not a problem that I like to kind of think about too much. Like the origin of life, it's a fascinating problem, but it's not physics, and I just don't love it.
It's the same reason you don't love. I thought you're a musician, so yeah. Music is not physics either. So why are you so into
100% physics?
Yeah. Okay.
No. Look. In all seriousness, though, there are a few things that I really, really enjoy. I genuinely enjoy physics. I genuinely enjoy music. I genuinely, enjoy martial arts, and I genuinely enjoy my family. I should have said that all in a reverse order or something. But I like to focus on these things and not worry too much about everything else. You know what I mean?
Yes.
Just because there is like you said earlier, there's a time constraint. You can't do it all.
There's many mysteries all around us. So, and they're all beautiful in different ways. To me, that thing I love is artificial intelligence. Mm-hmm. That perhaps I love it because eventually I'm trying to suck up to our future overlords. The question of, you said there's a lot of kind of little pieces of evidence for this thing that's Planet 9. If we were to try to collect more evidence or be certain, like a paper that says, like, you drop it, clear, we're done. What does that require? Does that require us sending probes out, or do you think we can do it from telescopes here on Earth? What are the different ideas for conclusive evidence for Planet 9?
The moment Planet 9 gets imaged from a telescope on Earth, it's done. I mean, it's just there.
Can you clarify? Because you mentioned that before. From an image, would you be able to tell?
Yes. So from an image, the moment you see something that is reflecting sunlight back at you, and you know that it's hundreds of times as far away from the sun as is the Earth, you're done.
So you're thinking, so basically, if you have a really far away thing that's big, 5 times the size of Earth, that means that's Planet 9.
That is Planet 9.
Could there be multiple objects like that? I guess
in principle, yeah. I mean, there's no law of physics that doesn't allow you to have multiple objects. There's also no evidence at present for there being multiple objects.
I wonder if it's possible. So it's like, just like we're finding exoplanets, whether given the size of the Oort cloud, there's basically, it's rarer and rarer, but there's sprinkled Planet 9, 10, 11, 12, like these.
Yeah.
Some
got 13.
Yeah, it goes after that. I can just keep counting. So like just something about the dynamic system, like it becomes lower and lower probability event, but they gather up, like they become, would they become larger and larger, maybe something like that. And I wonder if like discovering Planet 9 will just like be almost like a springboard. It's like, well, what's beyond that?
It's entirely plausible. The Oort cloud itself probably holds about 5 Earth masses or 7 Earth masses of material, right? So it's not nothing, and it all ultimately comes down to at what point will the observational surveys sample enough of the solar system to kind of reveal interesting things. Mm-hmm. There's a great analogy here with Neptune and the story of how Neptune was discovered. Neptune was not discovered by looking at the sky, right? It was discovered mathematically, right? So, the orbit of Uranus, when Uranus was found, this was 1781. It's the kind of tracking of both the tracking of the orbit of Uranus as well as the reconstruction of the orbit of Uranus immediately revealed that it was not following the orbit that it was supposed to, right? The predicted orbit deviated away from where it actually was. So in the mid-1800s, right, a French mathematician by the name of Urbain Le Verrier did a beautifully sophisticated calculation which said, if this is due to gravity of a more distant planet, then that planet is there. Mm-hmm. Okay. And then they found it. But the point is, the understanding of where to look for Neptune came entirely out of celestial mechanics. The case with Planet 9 is a little bit different because what we can do, I think, relatively well is predict the orbit and mass of Planet 9. We cannot tell you where it is on its orbit. The reason is we haven't seen the Kuiper Belt objects complete an orbit, their own orbit, even once, because it takes 4,000 years. But, I plan to live on as an AI being, and, I'll be tracking those orbits as...
So it takes 4,000 or 5,000 years. I mean, it doesn't have to be AI. It could be longevity. There's a lot of really exciting genetic engineering research. So you'll just be a brain waiting for your brain waiting for the orbit to complete for the basic Kuiper Belt objects.
That's right. That's like kind of the worst reason to want to live a long time, right? Just like, can the brain like smoke a cigarette?
I know, right?
Can you
It's just like
light one up while you're waiting, or?
But you're making me actually realize that the one way to explore the galaxy is by just sitting here on Earth and waiting. So if we can just get really good at waiting, it's like Oumuamua or these interstellar objects that fly in. You can just wait for them to come to you. Same with the aliens. You can wait for them to come to you. If you get really good at waiting, then that's one way to do the exploration, because eventually the thing will come to you. Maybe that's maybe the intelligent alien civilizations get much better at waiting, and so they all decide, so game theoretically, to start waiting, and it's just a bunch of like ancient intelligent civilizations of aliens all throughout the universe. They're just sitting there waiting for each other.
Look, you can't just be good at waiting. You got to know how to chill. Okay, like you can't just like sit around and do nothing. You got to be you got to know how to chill.
I honestly think that as we progress, if the aliens are anything like us, we enjoy loving things we do, and it's very possible that we just figure out mechanisms here on Earth to enjoy our life, and we just stay here on Earth forever, that exploration becomes less and less of an interesting thing to do. And so you basically, wait and chill. You get really optimally good at chilling, and thereby exploring is not that interesting. So in terms of 4,000 years, would be nothing for scientists. We'll be chilling, and just all kinds of scientific explorations will become possible because we'll just be here on Earth.
So chill.
So chill. You have a paper out recently, because you already mentioned some of these ideas, but I'd love it if you could dig into it a little bit.
Yeah, of course.
The injection of inner Oort cloud objects into the distant Kuiper Belt by Planet 9. What is this idea of Planet 9 injecting objects into the Kuiper Belt?
Okay, let me take a brief step back and say, when we do calculations of Planet 9, when we do the simulations, as far as our simulations are concerned, sort of the Neptune, like kind of the trans-Neptunian solar system is entirely sourced from the inside. Namely, the Kuiper Belt gets scattered by Neptune, and then Planet 9 does things to it and aligns the orbits and so on. And then we calculate what happens on the lifetime of the solar system, yada, yada, yada. During the pandemic, one of the kind of questions we asked ourselves, and this is indeed something Mike and I, Mike Brown, who's a partner in crime on this, and I do regularly, is we say, how can we, A, disprove ourselves, and B, how can we improve our simulations? Like, what's missing? And one idea that maybe should have been obvious in retrospect is that all of our simulations treated the solar system as some isolated creature, right? But the solar system did not form in isolation, right? It formed in this cluster of stars. And during that phase of forming together with thousands of other stars, we believe the solar system formed this almost spherical population of icy debris that sits maybe at a few thousand times the separation between the Earth and the Sun, maybe even a little bit closer. If Planet 9 is not there, that population is completely dormant. And these objects just slowly orbit the Sun. Nothing interesting happens to them ever. But what we realize is that if Planet 9 is there, Planet 9 can actually grab some of those objects and gravitationally re-inject them into the distant solar system. So we thought, okay, let's look into this with numerical experiments. Do our simulations. Does this process work? And if it works, what are its consequences? So it turns out, indeed, not only does Planet 9 inject these distant inner Oort cloud objects into the Kuiper Belt, they follow roughly the same pathway as the objects that are being scattered out. So there's this kind of two-way river of material. Some of it is coming out from, by Neptune scattering, some of it is moving in. And if you work through the numbers, you kind of at the end of the day that it has an effect on the best fit orbit for Planet 9 itself. So if you realize that the data set that we're observing is not entirely composed of things that came out of the solar system, but also things that got re-injected back in, then turns out the best fit Planet 9 is slightly more eccentric. That's kind of getting into the weeds. The point here is that the existence of Planet 9 itself provides this natural bridge that connects an otherwise dormant population of icy debris of the solar system with things that we're starting to directly observe.
So it can flow back. So it's not just a river flowing one way. It's maybe a smaller stream going back. And
backwash.
You want to backwash. You want to incorporate that into the simulations, into your understanding of those distant objects when you're trying to make sense of the various observations and so on.
Exactly.
That's fascinating. I got to ask you, some people think that many of the observations that you're describing could be described by a primordial black hole. First, what is a primordial black hole, and what do you think about this idea?
Yeah. So primordial black hole is a black hole which is made not through the usual pathway of making a black hole, which is that you have a star, which is more massive than 1.4 or so solar masses. And basically when it runs out of fuel, runs out of its nuclear fusion fuel, it can't hold itself up anymore, and just the whole thing collapses on itself, right? Yep. You create one, I guess, simple way to think about it is you create an object with zero radius that has mass but zero radius, singularity. Now, such black holes exist all over the place in the galaxy. There's, in fact, a really big one at the center of the galaxy.
Yeah,
that
terrifies me.
That one's always looking at you when you're not looking. Okay, right? It's always talking about you.
And when you turn off the lights, it wakes up.
That's right. But so such black holes are all over the place. When they merge, we get to see, incredible gravitational waves that they emit, et cetera, et cetera. One kind of plausible scenario, however, is that when the universe was forming, basically during the Big Bang, you created a whole spectrum of black holes, some with masses of 5 Earth masses, some with masses of 10 Earth masses, like the entire, mass spectrum size, the mass of asteroids. Now, on the smaller end, over the lifetime of the universe, the smaller ones kind of evaporate and they're not there anymore. At least this is what the calculations tell us. But 5 Earth masses is big enough to not have evaporated. So one idea is that Planet 9 is not a planet, and instead it is a 5 Earth mass black hole. And that's why it's hard to find. Now, can we right away from our calculations say that's definitely true or that's not true? Absolutely not. We can't. In fact, our calculations tell you nothing other than the orbit and the mass. And that means the black hole, it could be a 5 Earth mass, cup. It could be a 5 Earth mass hedgehog or a black hole or really anything that's 5 Earth masses will do, because the gravity of a black hole is no different than the gravity of a planet, right? If the sun became a black hole tomorrow, it would be dark, but the Earth would keep orbiting it. And like this notion that, black holes suck everything in, it's not. That's like a sci-fi notion.
Right, it's just mass. What would be the difference between a black hole and a planet in terms of observationally?
Observationally, the difference would be that you will never find the black hole, right? The truth is they're kind of, I'm actually not, I never looked into this very carefully, but there's some constraints that you can get just statistically. Say, okay, if the sun has a binary companion, which is a 5 Earth mass black hole, then that means such black holes would be extremely common. And, you could sort of look for lensing events, and then you say, okay, maybe that's not so likely. But, that said, I want to emphasize that there's a limit to what our calculations can tell you. And that's the orbit and the mass.
So I think there's a bunch, like Ed Witten, I think, wishes it's a black hole, because I think one exciting things about black holes in our solar system is that we can go there and we can maybe study the singularity somehow, because that allows us to understand some fundamental things about physics. If it's a planet, so planet 9, we may not, and we go there, we may not discover anything profoundly new. The interesting thing, perhaps you can correct me about planet 9, is like the big picture of it, the whole big story of the Kuiper Belt and all those kinds of things. It's not that planet 9 would be somehow fundamentally different from I don't know, Neptune, in terms of the kind of things we can learn from it. So I think that there's kind of a hope that it's a black hole because it's an entirely new kind of object. Yeah. Maybe you can correct me.
I mean, of course, here my own biases creep in because I'm interested, in planets around other stars. Mm-hmm. And I would say, I would disagree that, we wouldn't find things that would be truly, fundamentally new. Because as it turns out, the galaxy is really good at making 5 or 3 Earth mass objects, right? The most common type of planet that we see, that we discover orbiting around other stars, is a few Earth masses. Mm-hmm. In the solar system, there's no analog for that, right? We go from 1 Earth mass object, which is this one, and to skipping to Neptune and Uranus, which themselves are actually relatively poorly understood, I would say, especially Uranus from the interior structure point of view. If planet 9 is a planet, going there will give us the closest window into understanding what other planets look like. And I'll say this, that, planets kind of in terms of their complexity on some logarithmic scale fall somewhere between a star and an insect, right? And an insect is way more complicated than a star, right? Just there's all kinds of physical processes and really biochemical processes that occur inside of an insect that just make a star look like, somebody is like playing with a spring or something, right? So I think, it would be, arguably, more interesting to go to, planet 9 if it's a planet, because black holes are simple. They're just they're basically macroscopic, like particles. Yeah. Right. And so
just like a star that you mentioned in terms of complexity. So it's possible that planet 9, as opposed to being like homogeneous, is like super like heterogeneous. There's a bunch of cool stuff going on.
Absolutely.
That could give us an intuition. I never thought about that it's just basically Earth number 2 in terms of size, and starts giving us intuition that could be generalizable to Earth-like planets elsewhere in the galaxy.
I mean, Pluto is also, in this sense, like, Pluto is a tiny, tiny thing, right? Just like you would imagine as just a tiny ball of ice, like who cares? But the New Horizons images of Pluto reveal so much remarkable structure, right? They reveal glaciers flowing, and these are glaciers not made out of water ice, but, CO ice. It turns out at those temperatures, right, of like 40 or so Kelvin, water ice looks like metal, right? It just doesn't flow at all. But then ice made up of carbon monoxide starts to flow. I mean, there's just like all kinds of really cool phenomena that you otherwise just wouldn't really even imagine that occur. So, I mean, there's a reason why I like planets.
Well, let me ask you, I find, as I read, the idea that Ed Witten was thinking about this kind of stuff fascinating. So he's a mathematical physicist who's very interested in string theory, won the Fields Medal for his work in mathematics. So I read that he proposed a fleet of probes accelerated by radiation pressure that could discover a planet 9 primordial black hole's location. What do you think about this idea of sending a bunch of probes out there?
Yeah, look, the idea is a cool one, right? You go and you say, launch them basically isotropically, you track where they go. And if I understand the idea correctly, you basically measure the deflection and you say, okay, there must be something there since the probe trajectories are being altered.
Oh, so the measurement, the basic sensory mechanism is it's not like you have sensors on the probes. It's more like because you're very precisely able to measure the trajectory of the probes, you can then infer the gravitational fields. And
I think that's the basic idea. Back a few years ago, we had conversations like these with, engineers from JPL. They more or less convinced me that this is much more difficult than it seems, because you don't, at that level of precision, right? Things like solar flares matter, right? Solar flares, right, are completely chaotic. You can't predict where a solar flare will happen. That will drive radiation pressure gradients. You don't know where every single asteroid is. So like actually doing that problem, I think it's possible, but it's not a trivial matter, right?
Well, I wonder not just about Planet 9. I wonder if that's kind of the future of doing science in our solar system, is to just launch a huge number of probes. So like a whole order of magnitude, many orders of magnitude larger numbers of probes, and then start to infer a bunch of different stuff, not just gravity, but everything else.
So in this regard, I actually think there is a huge revolution that's to some extent already started, right? The standard kind of like time scale for a NASA mission is that you like propose it and it launches, I don't know, like 150 years after you propose. I'm over exaggerating, but it's just like some huge development cycle.
Yeah.
And it gets delayed 55 times. Like that is not going away, right? The really cutting edge things, you have to do it this way because you don't know what you're building, so to speak. But the CubeSat kind of world is starting to, provide an avenue for like, launching something that costs, a few $1 million and has a turnaround timescale of like a couple of years. You can imagine doing, PhD theses where you design the mission goes to where you're going, and you do the science all within a time span of 5-6 years. That has not been fully executed on yet, but I absolutely think that's on the horizon. And we're not talking a decade. I think we're talking like this decade.
Yeah, and the companies are accelerating all this with Blue Origin and SpaceX. And there's a bunch of more CubeSat-oriented companies that are pushing this forward. Let me ask you. Let me ask you on that topic. What do you think about either one? Elon Musk with SpaceX going to Mars. I think he wants SpaceX to be the first to put a first human on Mars. Mm-hmm. And then Jeff Bezos, got to give him props, wants to be the first to fly his own rocket out into space. So
wasn't there a guy who like built his rocket out of garbage?
Yeah.
This was like a couple years ago, and somewhere in the desert, he launched himself.
I'm not tracking this closely, but I think I am familiar with folks who built their own rocket to try to prove the Earth is flat.
Yes, that's the guy I'm talking about. Yeah, he also jumped some limousine.
Yeah. Truly revolutionary mind.
That's,
I mean, you have to greater men than either you or I. But what do you?
So look, it's been astonishing to watch how really over the last like decade, the commercial sector took over this, this industry that traditionally has really been like a government thing to do.
Motivated primarily by the competition between nations, like the Cold War.
Sure.
And now it's motivated more and more by the natural forces of capitalism.
Yes, that's right. So, okay, here I have many ideas about it. I think on the one hand, right, like what SpaceX has been able to do, for example, phenomenal. If that brings down the price of SpaceX and that turnaround timescale for space exploration, which I think it inevitably will, that's a huge boost to the human condition. The same time, right? If we're talking astronomy, right, there also it comes at a huge cost, right? And the Starlink satellites is a great example of that cost, right? At one point, in fact, I was just camping in the Mojave with a friend of mine, and they saw, this string of satellites just kind of like appear and then disappear into nowhere. So that is beginning to interfere with Earth-based observations. So I think there's tremendous potential there. It's also important to be responsible about how it's executed. Now, with Mars and the whole idea of exploring Mars, right? I don't have like strong opinions on whether a manned mission is required or not required, but I do think we need to the thing to keep in mind is that I generally kind of I'm not signed on, if you will, to the idea that Mars is some kind of a safe haven that we can, escape to, right? Mars sucks, right? Like living on Mars, if you want to live on Mars, like you can have that experience by going to the Mojave Desert and camping, and it's just like, it's just not a great.
Well, it's interesting, but there's something captivating about that kind of mission of us striving out into space, and by making Mars in some way habitable for at least like months at a time, I think would lead to engineering breakthroughs that would make life like in many ways much better on Earth. Like we'll come up with ideas we totally don't expect yet, both on the robotics side, on the food engineering side, on the maybe like we'll switch from we'll like there'll be huge breakthroughs in insect farming, as exciting as I find that idea to be. That in in the ways we consume protein, maybe it'll revolutionize. We do factory farming, which is full of cruelty and and torture of animals. Will revolutionize that completely because of our we shouldn't need to go to Mars to revolutionize life here on Earth, but at the same time, I shouldn't need a deadline to get shit done, but I do need it. And then the same way, I think we need Mars. There's something about the human spirit that loves that longing for
I agree with that thesis. The going to the moon, right, and that whole endeavor has captivated the imagination of so many, and it has led to incredible ideas, really, and probably in nonlinear ways, right? Not like, okay, we went to the moon, therefore some person here has thought of this and
yes.
In that similar sense, I think space exploration there's some real magnetism about it. And it's on a genetic level, right? Like we have this need to keep exploring, right? When we're done with a certain frontier, we move on to the next frontier. All that I'm saying is that I'm not moving to Mars to live there permanently, ever. And I think that I'm glad you noted the kind of degradation of the Earth, right? I think that is a true kind of the leading order challenge of our time.
Yeah, it's a great engineering.
Yeah, that's right.
It's a bunch of engineering problems. I'm most interested in space because, as I've read extensively, it's apparently very difficult to have sex in space, and so I just want that problem to be solved because I think once we solve the sex in space problem, we'll revolutionize sex here on Earth, thereby increasing the fun on Earth, and the consequences of that can only be good.
I mean, you've got a clear plan. Yeah. Right, and it sounds like
I'm submitting proposals to NASA as we speak.
That's right.
I keep getting rejected. I don't know why. Okay,
you need better diagrams,
better pictures. I should have thought of that. You a while ago mentioned that there's certain aspects in the history of the solar system and Earth that it could have resulted in an opaque atmosphere, but it didn't. We can see the stars. And somebody mentioned to me a little bit ago, it's almost like a philosophical question for you. Do you think human society would develop as it did or at all if we couldn't see the stars?
It would be drastically different. If it ever did develop. So I think some of the early developments, right, of like
fire and
fire. First of all, that atmosphere would be so hot because if you have an opaque atmosphere, the temperature at the bottom is huge. So we would be very different beings to start with. We'd have
But it
very
could be
different.
cloudy in certain kinds of ways that you could still get.
Okay, think about like a greenhouse, right? A
Yeah.
greenhouse is cloudy effectively, but it's super hot. It's hard to avoid having an atmosphere. If you have an opaque atmosphere, it's hard to, right? Venus is a great example, right? Venus is, I don't remember exactly how many degrees, but it's hundreds in Celsius, right? It's not 100, it's hundreds. Even though it's only a little bit closer to the sun, that temperature is entirely coming from the fact that the atmosphere is thick.
So it's a sauna of sorts.
Yeah. You go there, you feel refreshed after you come back,
But if you stay there, I mean, okay, take that as an assumption. This is a philosophical question, not a biological one. So you have a life that develops under these extremely hot conditions.
Yeah. So let's see. So much of the early evolution of mankind was driven by exploration.
Yeah.
Right. And the kind of interest in stars originated in part as a tool to guide that exploration. Right. I mean, that in itself, I think would be a huge, a huge differential in the way that we, our evolution on this planet.
Yeah, I mean, stars, that's brilliant. So even in that aspect, but even in further aspects, astronomy just shows up in basically every single development in the history of science up until the 20th century. It shows up. So I wonder, without that, if we would even get like calculus.
Yeah, look, that's a great point. Newton in part developed calculus because he was interested in explaining Kepler's laws, right? In general, that whole mechanistic understanding of the night sky, right, replacing a religious understanding where you interpret, this is, this whatever fire god riding his, little chariot across the sky, as opposed to, this is some mechanistic set of laws, that transformed humanity and arguably put us on the course that we're on today, right? The entirety of the last 400 years and the development of kind of our technological world that we live in today was sparked by that, right? Abandoning an effectively, a non-secular view of the natural world and kind of saying, okay, this can be understood, and if it can be understood, it can be utilized. We can create our own variants of this. Absolutely, we would be a very, very different species without astronomy. This, I think, extends beyond just astronomy, right? There are questions like, why do we need to spend money on X, right? Where X can be anything, like paleontology, right?
The mating patterns of penguins.
Yeah, that's
essential.
That's right. I think, there's a tremendous underappreciation for the usefulness of useless knowledge, right? I mean,
that's brilliant.
I didn't come up with this. This is a little book by the guy who started the Institute for Advanced Studies, but it's so true. So much of the electronics that are on this table, right, work on Maxwell's equations. Maxwell wasn't sitting around in the 1800s saying, I hope one day, we'll make, a couple mics so, a couple guys can, have this conversation, right? Yeah. That wasn't at no point was that the motivation. And yet, it gave us the world that we have today. And the answer is, if you are a purely pragmatic person, if you don't care at all about kind of the human condition, none of this, the answer is you can tax it, right? Like useless things have created way more capital than useful things.
And the sad thing, I mean, first of all, it's really important to think about, and it's brilliant in the following context. Like Neil deGrasse Tyson has this book about the role of military-based funding in the development of science. And then so much of technological breakthroughs in the 20th century had to do with humans working on different military things. And then the outcome of that had nothing to do with military. It had some military application, but their impact was much, much bigger than military.
The splitting of the atom is a kind of a canonical example of this. We all know the tragedy that, arises from splitting of the atom. And yet, so much, I mean, the atom itself does not care for what purpose it is being split. So
I wonder if we took the same amount of funding as we used for war and poured it into like totally seemingly useless things, like the mating patterns of penguins, we would get the internet anyway.
I think so. And perhaps more of the internet would have penguins.
Well, so we're both joking, but in some sense, like I wonder, it's not the penguins, because penguins is more about sort of biology, but all useless kind of tinkering and all kinds of in all kinds of avenues, and also because military applications are often burdened by the secrecy required. So it's often like so much the openness is lacking. And if we learned anything for the last few decades, is that when there's openness in science, that accelerates the development of science.
That's right. That's true. The openness of science truly, it benefits everybody. The notion that if, I share my science with you, then you're going to catch up and like know the same thing. That is a short-sighted viewpoint, because if you catch up and you open, you discover something, that puts me in a position to do the next step, right? It's just, so I absolutely agree with all of this. I mean, the kind of question of like military funding versus non-military funding is obviously a complicated one, but at the end of the day, I think we have to get over the notion as a society that we are going to, pay for this and then we will get that, right? That's true if you're buying like, I don't know, toilet paper or something, right? It's just not true in the intellectual pursuit. That's not how it works. And sometimes it'll fail, right? Like sometimes, like a huge fraction of what I do, right? I come up with an idea, I think, oh, it's great. And then I work it out. It's totally not great, right? It fails immediately.
Failure is not a sign that the initial pursuit was worthless. Right. So failure is just part of this whole exploration thing. And we should fund more and more of this exploration, the variety of the exploration.
Right. I think it was Linus Pauling or somebody from, that generation of scientists said that, a good way to have good ideas is to have a lot of ideas.
Yeah.
So I think that's true. If you are conservative in your thinking, if you worry about proposing something that's going to fail and, what if, there's no science police that's going to come and arrest you for proposing the wrong thing. And, it's also just like, why would you do science if you're afraid of, taking that step? It would be so much better to propose things that are plausible, they're interesting, and then for a fraction of them to be wrong than to just kind of, make incremental progress all your life, right?
Speaking of wild ideas, let me ask you about the thing we mentioned previously, which is this interstellar object, Oumuamua. Could it be space junk from a distant alien civilization?
You can't immediately discount that by saying absolutely it cannot. Anything can be space junk. I mean, from that point of view, can any of the Kuiper Belt objects we see be space junk? Anything on the night sky can in principle be space junk.
And Kuiper Belt would catch interstellar objects potentially and force them into an orbit if they're small enough?
Not the Kuiper Belt itself, but you can imagine Jupiter family comets being captured. So you can actually capture things. It's even easier to do this very early in the solar system, early in the solar system's life while it's still in a cluster of stars. It's unavoidable that you capture debris, whether it be natural debris or unnatural debris or just debris of some kind from other stars, that it's like a daycare center, right? Like everybody passes their infections on to other kids.
Yeah.
Oumuamua, there's been a lot of discussion about, there's been a lot of interest in this over, like, is it aliens or is it not? But let's, like, if you just kind of look at the facts, like what we know about it is it's kind of like a weird shape, and it also accelerated, right? Like that's the two, those are the two interesting things about it. There are puzzles about it, and perhaps the most daring resolution to this puzzle is that it's not, aliens, or it's not like a rock. It's actually a piece of hydrogen ice. Right? So this is a friend of mine, Daryl Seligman and Greg Laughlin came up with this idea where that in giant molecular clouds that are just clouds of hydrogen, helium, gas that live throughout the galaxy, at their cores, you can condense ice to become these hydrogen, icebergs, if you will. And then that explains many of the aspects of, in fact, I think that explains all of the Oumuamua mystery, how it becomes elongated, because basically the hydrogen ice sublimates, and kind of like a bar of soap that, slowly kind of elongates as you strip away the surface layers. How it was able to accelerate because of a jet that is produced from, the hydrogen coming off of it, but you can't see it because it's hydrogen gas. Like all of this stuff kind of falls together nicely. I'm intrigued by that idea, truly, because it's like, if that's true, that's a new type of astrophysical object.
And it would be produced by, what's the monster that produced it initially, that kind of object?
So this is giant molecular clouds. They are everywhere. I mean, the fact that they exist is not.
Are they rogue clouds, or are they part of like an Oort cloud?
No, they're rogue clouds. Yeah,
they're just floating about?
Yeah, so if you go, like, a lot of people imagine the galaxy as being a bunch of stars, right? And they're just orbiting, right? But the truth is, if you fly between stars, you run into clouds.
That don't have any large object that creates orbits. So they're just floating about.
They're just floating.
But why are they floating together? Or they just float together for a time and not?
Well, so these eventually become the nurseries of stars. So as they cool, they contract and then collapse into stars or into groups of stars. But some of them, the starless molecular clouds, according to the calculations that Daryl and Greg did, can create these like icicles of hydrogen ice.
I wonder why they would be flying so fast. Because they seem to be moving pretty fast at a quick pace. Oumuamua, yeah.
That's just because of their acceleration due to the sun. If you stop, I mean, it's like take something really far away, let it go, and the sun is here. By the time it comes close to the sun, right, it's moving pretty fast. So that's an attractive explanation, I think, not so much because it's cool, but it makes a clear prediction, right, of when Vera Rubin Observatory comes online next year or so, we will discover many, many more of these objects, right? And they have, so I like theories that are falsifiable, right? Not just testable, but falsifiable. It's good to have a falsifiable theory where you can say that's not true. Aliens is one that's fundamentally difficult to say, no, that's not aliens.
Well,
right?
The interesting thing to me, if you look at one alien civilization, and then we look at the things it produces, in terms of if we were to try to detect the alien civilization, there's like, say there's 10 billion aliens, there would probably be trillions of dumb drone type things produced by the aliens, and then be many, many, many more orders of magnitude of junk. So like if you were to look for an alien civilization, in my mind, you would be looking for the junk. That's the more efficient thing to look for. So I'm not saying Oumuamua has any characteristics of space junk, but it kind of opened my eyes, like, to the idea that we shouldn't necessarily be looking to the queen of the ant colony. We should be looking at, I don't know, like traces of alien life that doesn't look intelligent in any way, may not even look like life. It could be just garbage. We should be looking for garbage.
Just generically. Just generic.
Well, garbage that's producible by unnatural forces. For me at least, that was kind of interesting, because if you have a successful alien civilization, that we would be producing many more orders of magnitude of junk, and that would be easier potentially to detect.
Well, so you have to produce the junk, but you have to also launch it. So this is where, I mean, let's
Garbage
imagine
disposal.
Yeah, but let's imagine we are a successful civilization that has made it to space. We clearly have, right? And yes, we're in the infancy of that pursuit, but we've launched I don't know how many satellites. Probably, if you count GPS satellites, it must be at least thousands.
It's certainly thousands. I don't know if it's over 10,000, but it's on that order.
But it's on that, like, a large order of magnitude. How many of the things that we've launched will ever leave the solar system? I think 2.
It's 2 so far.
Well, maybe the Voyager 1, Voyager 2. I don't know if the Pioneer. So maybe 3.
There's also a Tesla Roadster out there.
That one, it will never leave the solar system. It'll just I think that one will eventually collide with Mars. That can be SpaceX's first Mars destination. But look, so there's an energetic cost to interstellar travel, which is really hard to overcome. And when we think about generically, what do we look for in an alien civilization? Oftentimes we tend to imagine that the thing you look for is the thing that we're doing right now.
Yeah.
Right. So I think that if I look at the future, right? I mean, for a while, like we were saying, okay, if aliens are out there, they must be broadcasting in radio, right? That radio, the amount that we broadcast in radio has diminished tremendously in the last 50 years, but we're doing a lot more computation, right? What are the signs of computation? Like, that's an interesting question to ask, right? Where, I don't know, I think something on the order of a few percent of the entire electrical grid last year went to mining Bitcoin. Right.
Well, there could be a lot of, in the future, different consequences of the computation, which, I mean, I'm biased, but it could be robotics. It could be artificial intelligence. So we may be looking for intelligent looking objects. Like, that's what I meant by probes, like things that move in kind of artificial ways.
But the emergence of AI is not an if, right? It's happening right in front of our eyes, and the energetic costs associated with that are becoming, a tangible problem. So I think, if you imagine kind of extrapolating that into the future, right? What are the, what becomes the bottleneck, right? The bottleneck might be powering the AI, broadly speaking, not one AI, but powering that entire AI ecosystem. Right. So I don't know. I think, space junk is kind of, it's an interesting idea, but it's heavily influenced by like sci-fi of 1950s, where by 2020, we're all like flying to the moon. And so we produce a lot of space junk. I'm not sure if that's the pathway that alien civilizations take. I've also never seen an alien civilization.
That's true. Anything. But if your theory of chill turns out to be true, and then we don't, we don't necessarily explore, we seize the exploration phase of like alien civilizations quickly seize the exploration phase of their efforts, then perhaps they'll just be chilling in a particular space, expanding slowly, but then using up a lot of resources, and then have to have a lot of garbage disposal that sends stuff out. Yeah. And the other idea was that it could be a relay that you'll almost have like these GPS like markers that you send throughout, which I think is kind of interesting. It's similar to this probe idea of sending a large number of probes out to measure gravitational, to measure basically, the gravitational field essentially. I mean, a lot of people at Caltech or and MIT are trying to measure gravitational fields, and there's a lot of ideas of sending stuff out there that accurately measures those gravitational fields to have a greater understanding of the early universe. But then you might realize that communication through gravity is actually much more effective than radio waves, for example, something like that. And then you send out, I mean, okay, if you're an alien civilization that's able to have gigantic masses, like basically,
we're getting there as a civilization.
No, we're not even close.
Well, I mean,
no, okay, yeah, okay. I mean, like, be able to sort of play with black holes, that kind of thing. So we're talking about a whole nother different order of magnitude of masses. Then it may be very effective to send signals via gravitational waves.
My sense is that all of these things are genuinely difficult to predict, and I don't mean like to kind of shy away. I really mean if you take imagination of what the future looked like from 500 years ago, right? It is so hard to conceive of the impossible, right? So it's almost like it's almost limiting to try and imagine things that are an order of magnitude, or 2 orders of magnitude ahead in terms of progress, just because you mentioned cars before. If you were to ask people what they wanted in 1870, it's faster buggies. Right. So I think the whole like kind of, alien conversation inevitably gets limited by our entire kind of collective astrophysical lack of imagination. If you know what I mean.
So to push back a little bit, I find that it's really interesting to talk about these wild ideas about the future, whether it's aliens, whether it's AI, with brilliant people like yourself who are focused on very particular tools of science we have today to solve very particular, like rigorous scientific questions. And it's almost like putting on this wild, dreamy hat, like some percent of the time, and say, like, what would alien civilizations look like? What would alien trash look like? Well, what would our own civilization that sends out trillions of AI systems out there, like HAL 9000, but 10,000 out there, what would that look like? And you're right, any one prediction is probably going to be horrendously wrong, but there's something about creating these kind of wild predictions that kind of opens up.
No, there's a huge magnetism to it, right? And some of it, I mean, some of the Jules Verne novels did a phenomenal job predicting the future, right? That actually was a great example of what you're talking about, right? Allowing your imagination to run free. I mean, I just hope there's dragons.
I love dragons.
Yeah, dragons are the best.
But see, the cool thing about science fiction and these kinds of conversations, it doesn't just predict the future. I think some of these things will create the future. Planting the idea. This is how the humans are amazing. Like, fake it till you make it. Humans are really good at taking an idea that seems impossible at the time, and for any one individual human, that idea is like it's like planting a seed that eventually materializes itself. Yeah. It's weird. It's weird how science fiction can create science,
and drive some of
it drives the science.
I agree with you, and I think in this regard, I'm like a sucker for sci-fi. It's all I listen to like now when I run, and some of it is completely implausible, right? And it's just like, I don't care. It's both entertaining and it's just like, it's imagination. You know about the Black Clouds book? I think this is by Fred Hoyle. This has great connections with sort of a lot of the advancements that are happening in NLP right now, right? With transformer models and so on. But it's this black cloud shows up in the solar system, and then people try to send radio, and then it learns to talk back at you.
Wow.
So anyway, we don't have to talk at all about it, but it's something worth checking out.
With that on the alien front, with the black cloud, to me, exactly on the NLP front, and also just explainability of AI, it's fascinating. Just the very question, Stephen Wolfram looked at this with the movie Arrival. It's like, what would be the common language that we would discover? The reason that's really interesting to me is we have aliens here on Earth now. Japanese. Well, yeah.
Japanese is the obvious answer.
Japanese, yeah, that would be the common. Maybe it would be music, actually. That's more likely. It wouldn't be a language. It would be art that they would communicate. But, I do believe that we have, I'm with Stephen Wolfram on this a little bit, that to me, computation, like programs we write, that, that they're kind of intelligent creatures. And I feel like we haven't found the common language to talk with them. Like our little creations that are artificial are not born with whatever that innate thing that produces language with us. And like coming up with mechanisms for communicating with them is an effort that feels like it will produce some incredible discoveries. You can even think of, if you think that math has discovered, mathematics in itself is a kind of...
Oh yeah, it's an innate construction of the world we live in. I think we are, a part of the way there, because pre-1950, right, computers were human beings that would carry out arithmetic, right? And I think it was Ulam who worked in Los Alamos at the time, like towards the end of the Second World War. Wrote something about how, in the future, right, computers will not be just arithmetic tool, but will be truly an interactive, thing with which you could do experiments, right? At the time, the notion of doing an experiment, not like in the lab with some beakers, but an experiment on a computer, designing an experiment, a numerical experiment, was a new one. That's like, 70% of what I do is I design, I write code, terrible code to be clear, but I write code that creates an experiment, which is a simulation. So in that sense, I think we're beginning to interact with the computer in a way that you're saying, not as just a, fancy calculator, not as just a, call and request type of thing, but something that can generate insights that are otherwise completely unattainable, right? They're unattainable by doing analytical mathematics.
Yeah, and there's like with the AlphaFold 2, we're now starting to crack open biology. So being able to simulate at first trivial biological systems and hopefully down the line complex biological systems. Right. My hope is to be able to simulate psychological, like sociological systems, like humans. I've, a large part of my work at MIT was on autonomous vehicles, and the fascinating thing to me was about pedestrians. Human pedestrians interacting with autonomous vehicles and simulating those systems without murdering humans would be very useful, but nevertheless is exceptionally difficult.
Yeah, I would say so. When is my Mustang going to drive itself? Right. It's, I'm not even joking. It's like,
yeah. It turns out it's much more difficult than we imagined. Yeah. And I suppose that's the kind of the progress of science is just like, going to Mars. It's probably going to turn out to be way more difficult than we imagine. Sending out probes to investigate Planet 9 at the edge of our solar system might turn out to be way more difficult than we imagine, but we do it anyway. Yeah. And we figure it out in the end.
It's actually, Mars is sending humans to Mars is way more complicated than sending humans to the moon. You'd think, just like naively, both are in space. Who cares? Like, well, if you go there, why don't you go there? just life support is an extremely expensive thing. Yeah.
There's a bunch of extra challenges, but I disagree with you. I would be one of the early people to go. I used to think not.
Yeah.
I used to think I would be one of the first maybe million to go once you have a little bit of a society. I think I'm upgrading myself to the first like 10,000.
Yeah, that's right. Front of the cabin. Yeah.
Not completely front, but like it would be
Yeah.
interesting to die. I'm okay with death. Sucks, but I kind of like the idea of dying on Mars.
Of all the places to die, I gotta say, in this regard, like, I don't want to die on Mars.
You don't.
No, I would much rather die on Earth. I mean, death is fundamentally boring, right? Like, death is a very boring experience. I mean, I've never died before, so I don't know from firsthand experience.
As far as you know.
Yeah.
It could be a reincarnation, all those kinds of things. So you mean where would you die if you had to choose?
Oh man. Okay, so
And
you know, I would definitely, you know, there's a question of who I'd want to die with.
Mm.
You know, I'd prefer not to die alone. But like, you know, surrounded by family would be preferable. Where? I think northern New Mexico. And I'm not even joking. Like, this is not a random, it's just like,
would that be your favorite place on Earth?
not necessarily like favorite place on earth to you know, reside at, you know, indefinitely, but it is one of the most beautiful places I've ever been to. So, you know, there's something, I don't know, there's something attractive about going, you know,
Returning to nature in a beautiful place. Let me ask you about another aspect of your life that is full of beauty: music.
Okay.
You're a musician. The absurd question I have to ask: what is the greatest song of all time?
Oh,
Objectively speaking,
the greatest song of all time.
I suppose
Yeah.
that could change moment to moment, day to day. But if you were forced to answer for this particular moment in your life, that's something that pops to mind. This could be both philosophically, this could be technically as a musician, like what you enjoy, maybe lyrics. Like for me, it's lyrics is very important. So
Absolutely.
I would probably, it would be, my choice would be lyrics based.
I don't want to answer in terms of just technical, you know, technical prowess. I think technical prowess is impressive, right? It's just like, it's impressive what can be done. I wouldn't place that into the category of the greatest music ever written. Some of the classical music that's written is undeniably beautiful, but I don't want to consider that category of music either, just because, you know, so if I was to limit the scope of this philosophical discussion to, you know, the kind of music that I listen to, you know, probably What's My Age Again by Blink-182. It's just, you know, it's a solid one. It's got, you know.
Said nobody ever. That's a good song. It's, I don't really know if you're joking.
No, I am joking. It's a good one, but it's yeah. I mean,
Nickelback is a close second. Yeah. What's my age again?
Yeah.
Oh, yeah.
No, I mean, it would probably, you know, songwriting wise, I think the Beatles came pretty close to.
Were they influential to you?
Absolutely.
Like the Beatles.
Yeah. Love the Beatles. I love the Beatles.
Let It Be, Yesterday. Yeah.
Like I think Strawberry Fields Forever is one of, you know what one of my favorite Beatles songs is? It's you know, In My Life, right? That song, it's hard to imagine how whatever a 24-year-old who wrote that is. It is one of the most introspective pieces of music ever. You know, I'm a huge Pink Floyd fan. And so I think, you know, if you were to, you can sort of look at the entire Dark Side of the Moon album as, you know, getting pretty close up there to the pinnacle of what, you know, can be created. So, you know, Time's a great song.
Yeah.
Time's a great song.
There's just the entirety of just the instruments, the lyrics, the feeling created by a song. Like Pink Floyd can create feelings, the entire experience. I mean, you have that with The Wall of just transporting you into another place. Songs not many songs could do that as well. Not many artists can do that as well as Pink Floyd did.
there are a lot of bands that you can kind of say, oh yeah, like if you take Blink 182, right? If you have no idea, like if you are listening to sort of that type of pop punk for the first time, it's difficult to differentiate between Blink 182 and like Sum 41 and the thousand of other like lesser known bands that all sounded, they all had that sparkling production feel. They all kind of sounded the same, right? With Pink Floyd, it's hard to find another band that you're like, well, is this one Pink Floyd? Or like, when you're listening to Pink Floyd, what you're listening to.
The uniqueness, that's fascinating. You know, in the calculation of the greatest song and the greatest band of all time, you could probably actually quantify this like scientifically, is like how unique, if you play different songs, how well are people able to recognize whether it's this band or not? And that, you know, that's probably a huge component to greatness. Like if the world would miss it if it was gone.
Yes. So,
but there's also the human story things. Like I would put Johnny Cash's cover of Hurt as one of the greatest songs of all time. And that has less to do with the song.
But your interaction with it.
With it, but also the full story of the human. So like, it's not just, if I just heard the song, it'd be like, okay, but if it's the full story of it, also the video component for that particular song. So like that, you can't discount the full experience of it.
Absolutely. You know, I have no confusion about about being, anywhere, in that lane. But I just like, I sometimes think about, music that is being produced today oftentimes feels like kind of clothes that you buy at like H&M and you wear 3 times before they rip and you throw away. So like, so much of it is not bad. It's just kind of forgettable, right? Like the fact that we're talking about Pink Floyd in 2021 is in itself an interesting question. Why are we talking about Pink Floyd? Right? There's something unforgettable about them and unforgettable about the art that they created.
That could be the markets that like, so Spotify's created this kind of market where the incentives for creating music that lasts is much lower because there's so much more music.
Right.
You just want something that shines bright for a short amount of time, makes a lot of money and moves on. And the same thing you see with the news and all those kinds of things. We're just living in a shorter and shorter like time scale in terms of our attention spans. And that nevertheless, when we look at the long arc of history of music, perhaps there will be some songs from today that will last as much as Pink Floyd. We're just unable to see it.
Yeah, just the collected works of Nickelback.
Exactly. You never know. You never know. Justin Bieber, it could have. It could be a contender. I've recently started listening to Justin Bieber just to understand what people are talking about, and I'll just keep my comments to myself on that one.
It's too good to explain in
the words cannot capture the greatness that is the Biebs. You as a musician. So you write your own music, you play guitar, you sing. Maybe can you give an overview of the role music has played in your life? You're a world-class scientist, and so it's kind of fascinating to see somebody in your position who is also a great musician and still loves playing music.
Yeah, well, I wouldn't call myself a great musician.
One of the best of all time. Yeah.
That's right.
Like we were saying offline, confidence is like the most essential thing about being a rock star.
Exactly. It's the confidence and kind of like moodiness, right?
Yeah.
Look, I mean, music plays an absolutely essential role in everything I do because if I stop playing for one reason or another, say I'm traveling, I notably lose creativity in every other aspect of my life, right? There's something, I don't view, playing music as a separate endeavor from doing science or doing whatever. It's all part of that same creative thing, which is distinct from, I don't know, pressing a button or like, you know,
So it's not a break from science. It's a part of your science.
It's absolutely is a part of it's I would say, you know, it's a thing that enables the science, right? The science would, you know, suck even more than it does already without the music.
And that means like the creating of the writing of the music, or is it just even playing other people's stuff? Is it the whole
both.
of it?
Yeah, it's definitely both. Yeah, and also just, you know, I love to play guitar, love to sing. You know, my wife tolerates my screeching singing, you know, and even kind of likes it. So
people should check out your stuff. You have a great voice, so I love your stuff. Is there something you're super busy? Is there something you can say about practicing for musicians, for guitar, for you're also in a band, so like that whole how you can manage that? Is there some tricks? Is there some hacks to being a lifelong musician while being like super busy?
So I would say, you know, the way that I optimize my life is I try to do, you know, the thing that I'm passionate about in a moment, and put that at the top of the priority list. Mm-hmm. There are moments when, you know, you feel inspired to play music, and if you're in the middle of something, if that can be put on hold, just do it, right? There are times when you get inspired about something scientific. You know, I do my best to drop everything, go into that, you know, mode of that isolated mode, and execute upon that. So it's a chaotic, you know, I think I have a pretty chaotic lifestyle where I'm always doing kind of multiple things and jumping between what I'm doing. But at the end of the day, it's not like, you know, those moments of inspiration are actually kind of rare, right? Like mm-hmm. most of the time, all of us are just doing kind of doing the stuff that needs to get done. If you do the disservice to yourself of saying, "Oh, I'm inspired to, you know, do this calculation, figure this out, but I've got to answer email or right. just like do something silly," you know, that is nothing more than disservice. And also, like, I have some social media presence, but I mostly stay off of, you know, social media to, you know, just frankly, because like I don't enjoy the mental cycles that it takes over.
It robs you of that those precious moments mm-hmm. that could be filled with inspiration in your other pursuits. But there's something to, maybe you and I are different in this. Like I try to play at least 10 minutes of guitar every day. Mm-hmm. Like almost on the technical side, like keeping that base of basic competence going. And I mean, the same way like writers will get in front of a paper no matter what, that kind of thing. It just feels like that for my life has been essential to the daily ritual of it. Otherwise, days turn into weeks turn into months, and you haven't played guitar for months.
No, I understand. For me, I think it's been like, if we have a gig coming up, we'll definitely
you need deadlines.
yeah, that's right. No, like we will sharpen up, definitely. You know, especially coming up to a gig. It's like, you know, we're not trying to make money with this. This is like just for the for that satisfaction of doing something well, mm-hmm. right? But overall, I would say I play guitar most days, right? Most days, and you know, when I put kids to sleep, I play guitar, you know, with them, and we like just make up random songs about, you know, about our cat or something. You know, like we just do kind of random stuff. But you know, music is always involved in that process.
Yeah, keeping it fun. You have Russian roots?
I sure do.
Were you born in Russia?
I was. Yeah.
When did you come here?
So I came to the U.S. in the very end of '99, but so I was like almost 14 years old. But along the way, we spent 6 years in Japan. So like we moved from Russia to Japan in 94 and then to the US in 99. So I did like elementary school.
Oh, interesting.
Middle school in Japan.
So elementary school in Japan.
Yeah.
So that's interesting, Dad. Do you still speak Russian?
Sure.
Okay. Ты по-русски говоришь?
Да, конечно.
Okay, maybe I'll let me ask you in Russian. Что ты помнишь о России? That'd be interesting to hear you speak a little Russian.
Да, в общем, в целом, я помню, то есть мне было 8, когда мы уехали, и, конечно, как сказать, помню в первом приближении все, включая вот переход, там, 91-й, 92-й год, вот этот турбулентный период, и еще, естественно, 93-й, то есть еще я очень хорошо помню, как в какой-то момент сначала появилась пепси-кола, а потом появилась кока-кола. Я помню, я был лет, не знаю, 6, и я подумал, как так может быть, что кока-кола украла продукт и сделала то же самое. То есть я долго думал, что и пепси, и кока-колу изобрели типа в 92-м году.
So for people who don't speak Russian, Konstantin was talking about basically his first in 1992 interaction with capitalism, which is Pepsi. And at first he discovered Pepsi, and then he discovered Coke, and he was confused how such theft could occur.
Yeah, like an intellectual property theft. And remember, Pepsi arrived to the Soviet Union first, and there's some complicated story which I don't quite understand the details of. For a while, Pepsi like commanded submarines or something. Pepsi had like a fleet of Soviet submarines that they
were sponsoring tanks, and that's fascinating.
Yeah.
And I remember there's certain things that trickled in, like McDonald's. I remember that was a big deal.
Oh,
there's
yeah,
certain aspects of the West.
Absolutely. So I mean, we went to McDonald's. And we stood on, I mean, this is absurd, right? From kind of looking at it from today's perspective, but we stood in line for like 6 hours to get into this McDonald's. And, I remember inside it was just like 1 billion people. And I'm just taking a bite out of that Big Mac. And we're like, wow.
What was it an incredible experience for you? So, like, what is this taste of the West like? Did you enjoy it?
I enjoyed the fact that, I mean, this is getting into the weeds, but I really enjoyed the fact that the top of the bun had those seeds, and I remember how on the commercials, like the Big Mac would kind of bounce. Mm-hmm. I was like, the seeds, how do they inject the seeds into the bread? Like, amazing. Yeah. Right. So I think it was
artistry.
Yeah,
you enjoy the artistry of the culinary experience.
Exactly. It was the, food art that is the Big Mac.
Actually, I still don't know the answer to that. How do they get the sesame seeds on the
bun? It's better to not know the answer.
You just wonder at the mystery of it all. Yeah, I remember it being exceptionally delicious, but I'm with you. I don't know. You didn't mention how transformative Pepsi was, but to me, basically sugar-based stuff like Pepsi was or Coke. I don't remember which one we partook in, but that was an incredible experience.
Yeah. No, absolutely. And I think it's it was an important and formative period. I sometimes, I guess, rely on that a little bit, in my daily life, because I remember like the early 90s were real rough. Like my parents were kind of on the bottom of the spectrum in terms of financial well-being. So kind of like just when I run into trouble, not like money trouble, just any kind of trouble these days, it just kind of is not particularly meaningful when you compare it to that turbulent time of the early 90s. And the other thing is, I think there's like an advantage to being an immigrant, which is that you go through the mental exercise of changing your environment completely early in your life, right? You go, it's by no means, pleasant in the moment, right? But like going into Japanese elementary school, right? Like I didn't go to some like private, thing. I just went to a regular like Japanese public elementary school, and I was the non-Japanese person in my class. So just like the learning Japanese and just kind of.
So that's a super humbling experience in many ways. Were you like made fun of all that kind of stuff?
Oh, yeah.
Being the outsider.
Oh, absolutely. But, you kind of do that, and then you just kind of are okay with stuff. You know what I mean? And so like doing that again in middle school in the US, it was arguably easy because I was like, yeah, well, I've already done this before. So I think it kind of prepares you mentally a little bit for switching up for whatever changes that will come up for the rest of your life. So I wouldn't trade that experience really for anything. It's a huge aspect of who I am, and I'm sure you can relate to a lot of this.
Yes. Is there advice from your life that you can give to young people today, high school, college, about their career? Or maybe about life in general?
I'm not like a career coach by
life coach,
right? Like I'm definitely not a life coach. I don't have it all figured out, but I think there's a perpetual cycle of thinking that there's kind of like a template for success, right? Maybe there is, but in my experience, I haven't seen it, right? I would say people in high school, right? So much of their focus is on getting straight A's, filling their CV with this and this and this so that it looks impressive, right? That is not, I think, a good way to optimize your life, right? Do the thing that fills your life with passion. Do the thing that fills your life with interest, and do that perpetually, right? A straight A student is really impressive, but also somewhat boring, right? So I think injection of more of that kind of interest into the lives of young people would go a long way in just both upping their level of happiness and then just kind of ensuring that looking forward, they're not suffering from a perpetual condition of, I have to satisfy these check boxes to do well, right?
Because you can lose yourself in that whole process for the rest of your life. But it's nice if it's possible, like Max Tegmark was exceptionally good at this at MIT, figure out how you can spend a small part of your percent of your efforts such that your CV looks really impressive.
Yeah, absolutely. There's no, without a doubt, that's a baseline that you need to have.
And then spend most of your time doing like amazing things you're passionate about, but such that it kind of like Planet Nine produces objects that feed your CV slowly over time. So getting good grades in high school, maybe doing extracurricular activities, or in terms of for programmers, that's producing code that you can show up on GitHub, like leaving traces throughout your efforts such that your CV looks impressive to the rest of the world.
In fact, I mean, this is somewhat along the lines of what I'm talking about. See, getting good grades is important, but grades are not a tangible product.
Right.
You cannot show your A and have your A live a separate life from you. Code very much does, right? Music very much takes on, provided somebody else listens to it, right? Takes on a life of its own. That's kind of what I mean, right? Doing stuff that can then get separated from you is exceptionally attractive, right? It's like a fun. And
it's also very impressive to others. I think we're moving to a world where grades mean less and less. Like certifications mean less and less. Yeah. If you look at, especially again in the computing fields, getting a degree, finishing your currently just finishing your degree, whether it's bachelor's, a master's, a PhD, is less important than the things you've actually put out into the world.
Right.
And that's a fascinating kind of, that's great that in that sense, the meritocracy is in its richest, most beautiful form is starting to win out.
Yeah, it's weird because my understanding, and I'm not I don't know the history of science well enough to speak very confidently about this, but the advisor of my advisor of my advisor from undergrad, didn't have a PhD, right? So I think it was a more common thing back in the day, even in the academic sector, to, not have, Faraday. Faraday didn't know algebra, right? And drew diagrams about, magnetic fields, and his Faraday's law was derived entirely from intuition. So it is interesting to how the world of academia has evolved into you got to do this and then get PhD, then you have to postdoc once and twice and maybe thrice, and then you move on. So I do wonder if we're if there's a better.
I think we're heading
approach,
there, but it's a fascinating historical perspective. That we might have just tried this whole thing out for a while, where we put a lot more emphasis on grades and certificates and degrees and all those kinds of things. I think the difference historically is we can actually, using the internet, show off ourselves and our creations better and better and more effectively, whether that's code or producing videos or all those kinds of things.
That's right. You can become a certified drone pilot. It's true.
of all the things you want to pick, yeah, for sure. Or you could just fly, make YouTube videos that gets hundreds of thousands of views with your drone and with never getting a certificate. That's probably illegal. Don't do it. What do you think is the meaning of this whole thing? So you look at planets. Mm-hmm. They seem to orbit stuff without asking the why question. And for some reason, life emerged on Earth such that it led to big brains that can ask the big why question. Do you think there's an answer to it?
I'm not sure what the question is. What
meaning of life?
The meaning of life. It's 42.
It's 42.
Yeah. But, aside from that, it's, why... I think if the question you're asking is why we do all this, right?
Why we do all this?
It's part of the human condition, right? Human beings are fundamentally, I feel sort of stochastic and fundamentally interested in kind of expanding our own understanding of the world around us.
And creating stuff to enable that understanding. So we're stochastic, fundamentally stochastic. So there's just a bunch of randomness that really doesn't seem like it has a good explanation. And yet there's a kind of direction to our being that we just keep wanting to create and to understand.
That's right. I've met people that are, that claim to be anti-science, right? And yet in their anti-science, discussion, they're if you're so, scientific, then why don't you explain to me how, this works? And it always, there's that fundamental seed of curiosity and interest that is common to all of us. Yeah. That is absolutely what makes us human, right? And I'm in a privileged position of being able to, to have that be my job, right? I think as time evolves forward, and the kind of economy changes. I mean, we're already starting to see, a shift towards that type of, creative, enterprise as emerging, taking over a bigger and bigger chunk of the sector. It's not yet, I think, the dominant portion of the economy by any account. But if we compare this to some time when the dominant thing you would do would be to, go to a factory and do the same exact thing, right? I think, there's a tide there, and things are sort of headed in that direction.
Yeah, life's becoming more and more fun. I can't wait. Honestly, what happens
I can't wait
next?
to just chill.
Just chill.
The terminal point of this is to just chill and wait for those Kuiper Belt objects to complete one orbit.
I'm going to credit you with this idea. I do hope that we definitively discover proof that there is a Planet 9 out there in the next few years, so you can sit back with a cigar, a cigarette, or vodka or wine and just say, I told you so.
That's already happening. I'm going to do that later tonight.
Well, as I mentioned, confidence is essential to being a rock star. I really appreciate you explaining so many fascinating things to me today. I really appreciate the work that you do out there. And I really appreciate you talking with me today. Thanks, Konstantin.
It was a pleasure. Thanks for having me on.
Thanks for listening to this conversation with Konstantin Batygin. And thank you to Squarespace, Literati, Onnit, and I. Check them out in the description to support this podcast. And now let me leave you with some words from Douglas Adams in The Hitchhiker's Guide to the Galaxy. Far out in the uncharted backwaters of the unfashionable end of the western spiral arm of the galaxy lies a small, unregarded yellow sun. Orbiting this at a distance of roughly 92 million miles is an utterly insignificant little blue-green planet whose ape-descendant life forms are so amazingly primitive that they still think digital watches are a pretty neat idea. Thank you for listening, and hope to see you next time.